No, your face says, because now all the entire screen we are having well spaces, and it is a message for all actions will work and how you should link with your all-time seniors. And the same message I was telling yesterday. We are going to lose Charlie sir and then Srima sir from here, and next set of youngsters are going to be here, and that bridging. But now this is what happened. Now Lashmi Shankar, she seems to be very younger, and then Jindo sir was telling something like playing volleyball and all. Now that culture and all are almost gone from Devagiri and all. Now it's a different scenario. And then Rajib sir was here. Yeah, it's a very nice occasion. Yeah, we can. Father Manager also joined, and then why don't we start straight away?
Hand over, Mr. Hand over.
Thank you.
Am I audible? Hello?
Yeah, clear.
A warm welcome to Anatol. Well-measuring resource persons, distinguished guests, Principal Dr. Sabuki Thomas, delegate teachers, and dear friends. It's my pleasure to welcome you all to the international webinar on recent trends in physics, organized by the Department of Physics, St. Joseph College, Devagiri. The webinar aims at creating awareness among the students on the current developments in physics and foster a scientific temperament. The webinar will be an excellent platform for students to identify research opportunities in academic institutions and industry in and outside India. It's a matter of pride that the esteemed resource persons of the webinar are alumni of our department. The program is in honor of the contributions of our two towering faculty members, Professor Charlie Kattagan, HOD of Physics Department, and Dr. R. Srikumar, Associate Professor, whom are retiring soon from their official service. We are moving on to the inaugural ceremony. It's the mark of our undying tradition to invoke the God Almighty at the beginning of every session. I would like to call upon Vinaya for the prayer song.
Paripurnamam Jeevitam Saujanyamai Taru Ishvara Hridayachati Jeevan Parudevame Aradhana Paripurnamam Jeevitam Studi Paduvanikashayai Tirumundi Studi Paduvanikashayai Namadhari Kuli Olama Namadhari Kuli Olama Ashwasagan Madhavai Paripurna Jeevitam Saujanyamai Ishvara Hridayachati Jeevanin Parudevate Aradhana Paripurnam Jeevitam.
Let me take the privilege of inviting Dr. Meryl Matthew, Assistant Professor of St. Joseph College, Devagiri, for the welcome address.
Respected Principal Dr. Sabuki Thomas, Manager Father Biju Joseph, Vice Principal Father Anto N.G., our guests of honor, Professor Charlie Katakayam, Dr. Srikumar, Chair for this session, Dr. Reggie Philip, esteemed speakers, dear participants and colleagues. A very good afternoon to you all. On behalf of Department of Physics, St. Joseph's College, Devagiri, I welcome all the participants for today's webinar on recent trends in physics. It's a diversified topic shared by active researchers joining from different parts of the world. We would like to extend our warm welcome to our principal, Dr. Sabuki Thomas, Manager, Father Dr. St.Joseph, Vice Principal Father Anto NG. It is the strong support and encouragement of the principal and management which provide us with the enthusiasm to conduct such events. We would like to invite our guests of honor, two vibrant personalities, the towering faculty members, Professor Charlie Kattakayam, Head of the Department of Physics, and Dr. Sri Kumar, who are retiring from official service. Our deepest regret is that we missed an offline event during this pandemic. We would like to extend a warm welcome to Dr. Reggie Philip, Professor, Raman Research Institute, Bangalore, who accepted our invitation. It's a real privilege to have such an eminent faculty like him to chair our session. Dr. Reggie Philip, classmate and close friend of Sri Kumar sir, was always there for us, extending his support to staff and students of the department. We are really happy, privileged, and feel proud to welcome all the eminent speakers and guests who are our alumni from different parts of the world, from different walks of life, who have joined here to share their knowledge and experience with our student community. All speakers readily accepted the invitation for the webinar in honor, which announced their love and respect towards the retiring faculty members and department. I would like to invite our distinguished speakers, Dr. Jiddo Thomas, Scientific Officer F at Institute of Plasma Research, Gandhinagar, who was our student from 1995 to 2000, who did his pre-degree and degree at our institution. Dr. Sujin, Associate Professor, Department of Physics, IIT Delhi, who was our degree student of 1999 to 2002 batch. Dr. Karina B. Maliekal, postdoctoral researcher, Lund University, Sweden, who completed her BSc in 2009. Dr. Ashwati Balagopal, postdoctoral researcher, University of Wisconsin, USA. Dr. Vaishak CP, postdoctoral researcher, Czech Academy of Sciences, Prague. Both of them belong to our 2012 pass-out batch. They are classmates too. We are wholeheartedly welcome all of you. Your presence itself is an appreciation and encouragement to all of us. It's my pleasure to welcome all the delegates, including our distinguished alumni and faculty members and students from other institutions, colleagues and students who joined us. Once again, I welcome you all to this webinar. Thank you.
Thank you, ma'am. To walk safely through the maze of human life, one needs the light of wisdom and guidance of virtue. Let me invite our principal, Dr. Savuki Thomas, for the presidential address.
Savasara, mic on akilla. Mic on akam.
Thank you. Good afternoon. Yeah, it's really a wonderful occasion. And we have dear Father Manager, Father Biju Joseph, Father Vice Principal, Father Anto. Then we have the two very important personnel who will be disappearing from the Devagiri scenario. That is Professor Charlie Kattakayam and Professor Sri Kumar. And then all the distinguished guests, resource persons who could share and find time to be with this gang of youngest days. That includes a long list: Dr. Rajiv Phil, Dr. Jindo, Dr. Sujin Babu, Dr. Karina Maliakal, Dr. Ashwati Balkobal, Dr. Vaishak CP, and all the faculty members of physics department. And there's a long list of participants. I see around 100 join here. So it's a great occasion for the department. Though we are sad to say, to towering personalities of this college and department, they will be slowly disappearing, because this is there is a time, it is time to go, and they will be replaced by a new set of youngest days, definitely. But now how far that vacuum can be filled up and all, yeah, that only time will say. And to all the distinguished resource persons, what I would say, it was nice meeting you all in the computer panel now, and we hope that more and more future interactions with the department will come out, because now various forums are there, DBT and EST, and they're all hoping funding opportunities and all. Now with the advent of this corona, though it has affected the health of a lot of people, but it made possible to have almost all the entire college and different places are having internet facilities, and this kind of video conferencing is possible. So it offers a lot of positive spirit in the long run also, because now we can, college and also the students of this college also, definitely they can look forward to have more and more interactions with distinguished lecturers here. And what I go to tell to the students, your faculty members of the physics department should be congratulated for arranging this particular program. It was a dual function. One is paying homage to Charlie sir and Sriguma sir, and they planned in such a way, they talked with all the resource persons, and they arranged this program in such a way. Now interactions with within the group, and also for the students you are all watching who all are here, it's all a kind of opportunity and also hope for you from this department where you can reach. And also you can seek the help of alumni, distinguished alumni, because sometimes I many times used to ask many of the degree graduates who come to me for with the scholarship applications and all, how many internships have you taken? And often the answer is not so positive. So they all take the scholarship, internship opportunities are there, but they didn't use it. They could have approached many of, there are 5-6 people are here, could have approached, they could have done a wonderful project works and all, and it would have been helpful for in the long run also. So in the I think there may be first years and second years here. They also think like that, because a lot of candidates from the physics department, because physics is one of the most sought after course in the college, a lot of good applicants, meritorious students from different parts of Malabar specifically, I would say. But scholarship doesn't mean getting the funds alone. You have the funds to do more there. That is academic and scientific activity during your degree curriculum in the name of small projects. Whether it is there in your syllabus or not, don't bother. And for that, this alumni will definitely help you. You can seek their help, and definitely they will be happy to. Though I know all the scientists, they're all very busy scientists, but they will be happy to see a letter from their very college requesting for help. And then Professor Charlie and then Dr. Sriguma, they all can give good recommendation letters. And this is how the system works. But how you used it or not, I don't know. But anyway, it's a good occasion, maybe a good beginning also. So once again, I thank the entire department faculty for making this wonderful program, arranging this program. And it is going to be a meaningful program, because we have one talk today and then next day another person like that. So with these few words of because that is part of my duty, I say my thanks to the department members, faculty members, and to Charlie sir and Srima sir for being part of it, encouraging the department faculty members to do it, and for all the resource person to spare their time and to be with us. Thank you.
Thank you, sir. I cordially invite Reverend Father Dr. Sujin Joseph, the manager of St. Joseph College, Devagiri, for the inaugural address.
Is it audible to you?
Yes, sir.
Okay. Most respected Principal, Dr. Sabuke Thomas, Vice Principal and Accuracy Coordinator, Father Anto Enche, Head of the Department, Professor Charlie Kattagayam, Dr. Srigumar, Dr. Merrill Matthew, Chairperson of the program, Dr. Reggie Philip, Professor Raman Research Institute, Bangalore, resource persons and eminent alumni of Devagiri, especially of Physics Department, Dr. Chinta Thomas, Dr. Sujin Babu, Dr. Karina Maliakan, Dr. Ashwadi Balagopal, and Dr. Vaishak CP. Program coordinators, Mr. Abarnayan, Dr. Nijesh James, teachers, students, and other respected participants. Due to COVID-19 pandemic, actually we all are forced to go with online classes and different webinars and programs. Recently, the regular activities in the college are resumed partially. Classes are almost over and exams started for final years, and for some of them, it's over. Still, we have restrictions in physical gathering involving large number of people. So it is difficult to organize large gathering and real-time seminars. That's why we have been conducting webinars in these days. A lot of webinar sessions were organized by different departments in our college on different topics in these days. Today, the Department of Physics organized a webinar on the topic Recent Trends in Physics and a discussion on the prospects of research in physics. The significance of this webinar is that we especially honor two of our eminent teachers who retired from the service this year, Professor Charlie Kattagayam and Dr. Srigumar S. I feel grateful to be here on this occasion of honoring them, who retired from the active position in the college in these days. I congratulate the entire department, especially the coordinators, Mrs. Abarnayan and Dr. Nijesh James, in organizing this resourceful program in honor of our two great teachers. I think they are really honored by the presence of their own students as resource persons on this occasion. We have 5 eminent alumni as resource persons for these seminar series or for this seminar, who is doing their postdoctoral research in different countries. I feel cherished to say that we must respect all the valuable skills and knowledge of these two teachers. They have offered everything to the students to make them future leaders in the society. So we must thank them for their effort, sincerity, and hard work for making this institution appreciated by many. Professor Charlie Kattagayam has been here as a teacher and serving the students and institution for over 30 years now. And Dr. Srigumar was here for the last 25 years as a good teacher by imparting knowledge to the students' community while being with the institution always. Both of them were sincere, responsible, well-respected, and highly esteemed teachers. Both institution and students' community benefited from their generous, modest, and open-minded personalities. Actually, Professor Charlie and Dr. Sigma were a good example to the entire teaching community in showing how to be a role model by imparting knowledge and being with the students in overcoming their struggles. Today we have this webinar with highly interdisciplinary nature. We discuss on recent trends in physics. I hope that this webinar will be helpful to understand the latest developments in the field of physics. Panel discussions and deliberations are based on the emerging research topics in physics. Panelists and resource persons are from different branches of physics. Actually, they all are our esteemed alumni who is doing their research in different areas of physics in different research institutions across the world. So it is a proud movement for Devagiri to hear from our own alumni who have international exposure. I hope this webinar will be an excellent platform for researchers, scientists, and students to exchange their ideas. I appreciate the organizing committee, Mrs. Aparnayan and Dr. Nijesh James, and all the esteemed faculty members of the department for taking initiative to organize discussions on such an important topic and to honor our respected dear teachers. Once again, by wishing all the success for the program, I hereby declare that this webinar on recent trends in physics has inaugurated. Wish you all some fruitful sessions. I remain. Thank you. Thank you.
Thank you, Father. May I request Father Antoine, the Vice Principal of St. Joseph College, Devagiri, for the felicitation.
Hope I am audible to you.
Yes.
Respected Chair Dr. Sabuke Thomas, our Principal, Reverend Dr. St.Joseph, our Manager, Professor Charlie Kattakayam, Head of the Department of Physics, Dr. Sri Kumar, our Associate Professor, Department of Physics, St. Joseph's College, Devagiri, and Dr. Reggie Philip, the moderator of the webinar, and other eminent resource persons for today's webinar, respected teachers and my dear students and other distinguished participants of this international webinar. A very good afternoon to one and all. So at the outset, I would like to appreciate all the faculty members of the Department of Physics, St. Joseph's College, Devagiri, for organizing an international seminar on recent trends in physics. So I was thinking what is unique about this international seminar. Rather than the topic selected for the deliberations, what I found as unique in this seminar is the presence of the resource persons of this seminar. All the speakers who spoke before me have rightly mentioned that all the resource persons, I think, except the moderator, are the proud alumni of St. Joseph's College, Devagiri. So it's a moment of pride for St. Joseph's College, Devagiri in general, and the Physics Research Department of Physics at St. Joseph's College, Devagiri in particular. So these people are scientific officers, associate professors, and postdoctorate researchers in different parts of the country and also all across the world. So definitely it's just a matter of pride for us, and their presence itself speaks volumes, and their presence itself show that the caliber, the quality of this particular department. All the faculty members who are working here and also who have retired from the department can be proud about this great achievement. And as we know, today's international webinar is organized in honor of two eminent professors, Professor Charlie Kattakayam and also Dr. Sri Kumar. And Professor Charlie has been working here, serving this institute for the last 32 years, and Dr. Sri Kumar around 25, 26 years. So it's a pretty long period. I think it's a major chunk of their life they have spent on this campus, imparting knowledge to thousands of students. So I think it's a moment of realization, and it's a moment of fulfillment for these two teachers. The fact that their own students from across the world are coming together, and they are going to deliver their different expert talks on different topics. So, and also we know these two professors, they have served our college in many capacities, and they have considered this college as our second home, and they have considered the students as their own children. So the college has benefited a lot. The students of different generations have benefited a lot from these two professors. So I should say that St. Joseph's College Devagiri is so much obliged to these two great professors, and as Father Manager has rightly mentioned, they have set a good model for all of us, for the young teachers of St. Joseph's College Devagiri. So I hope I will get other platforms to appreciate them, to remember their services for the college. So today, I would like to thank on behalf of the college, these two great professors for their great service. And I also, once again, I would also thank and appreciate the members of the Department of Physics for organizing this seminar. And I also should thank on behalf of the college, the resource persons who have come up today, turned up today, because in spite of our busy schedule, receiving the invitation from the college, you graciously consented to be part of this seminar, and we are ready to present papers. And on behalf of the college, also I would like to extend our thanks to all the resource persons of today's function. So wishing you all a very fruitful international seminar. I remain. Thank you so much.
Thank you, Father. I invite Dr. Vinita Janathan, faculty at Department of Physics of St. Joseph College, for the vote of thanks.
Distinguished guests, honorable dignitaries, faculty members, teachers, students, and all other participants. Very good afternoon to all of you. It's my privilege for having been asked to propose a vote of thanks on this occasion of an international webinar conducted in honor of the contributions of our respected faculty members, Professor Charlie Kattakayam and Dr. Sri Kumar. We are extremely grateful to them for their valuable suggestions, opinions, and guidance for the different departmental activities. And on behalf of Department of Physics, let me take this opportunity to express my sincere gratitude to Dr. Reggie Phillip, Professor at Raman Research Institute, who is also the moderator of today's webinar. Thank you, sir, for sparing your valuable time to help us in making this event a success. I also wish to thank the speakers, the resource persons who have readily accepted our invitation to share with us their research findings and to enlighten us with their knowledge on the recent trends in physics. It's indeed a great honor for us that they are the alumni of our department. We are grateful to the principal, Dr. Sabu K. Thomas, the manager, Father Dr. Biju Joseph, and the vice principal, Father Andrew N.J., for their constant, enthusiastic support and cooperation. A special thanks to the organizing committee, teaching and non-teaching staff for their unflinching support and coordination. Last but not the least, our heartfelt thanks to our students and other participants for their active participation and contribution to make this webinar exemplary. Thank you everyone once again for your gracious presence. Thank you.
We are moving on to our technical section. I have immense pleasure to introduce our moderator of this event, Dr. Reggie Philip, Professor at Raman Research Institute at Bangalore. It has made several fundamental contributions to the field of nonlinear optics. He has 185 journals to his credit, guided 9 PhD students, published 3 book chapters, 1 US and 1 Indian patents. He was a reviewer to several international journals and was a prominent visiting scientist at University of Regensburg, University of Massachusetts, University of Central Florida, and also at Tata Institute of Fundamental Research, Mumbai. He served as a faculty at University of Kerala, Thiruvananthapuram. He served and also to the Sacred Heart College, Cochin, and was a research fellow at CUSAT. He was a member of several academic committees, academic council, board of studies, and few other institutions. With this brief introduction, I would like to welcome our moderator of this event, Dr. Reggie Philip, to this webinar. Over to you, sir.
Good afternoon, everyone, and thank you very much for those very kind words of introduction. My congratulations to the physics faculty and students of Devagiri College for organizing this seminar in the honor of Professor Charlie Kattakayam and Dr. R. Srikumar. And also my thanks for inviting me here to be the moderator of the scientific proceedings of today. I know both Professor Charlie and Dr. Srikumar for a long time. And during the several visits I had to the St. Joseph's College, Devagiri in the past, I had the opportunity to interact with Professor Charlie Kattakayam, and we had some very good, very interesting discussions, though brief, because my visits are usually brief. It's usually for a conference or giving a talk. So we had those brief discussions, but it was not difficult to understand that he was an excellent teacher and a beloved teacher of his students. And talking about Dr. Srikumar, we are friends for a very, very long time. I mean, we met for the first time in Cochin University Physics Department in 1985, in September 1985. We happened to be in the same MSc class, MSc Physics class there. And thereafter, we had the same guide for our PhD there itself. We were roommates at the Sanadana hostel of CUSAT. And later on, after PhD, our paths diverged. But nevertheless, I still had opportunity to come to Calicut, either to the college or to NIT or for some other visits. And almost always, I visited Srikumar and Mrs. Dr. Sumangala Srikumar at their home. And I was fortunate to receive their great hospitality on all those occasions. So today we are honoring both Professor Charlie and Dr. Srikumar on the occasion of their imminent retirement. And I wish both of them a very great time ahead retirement is actually the beginning of doing all the things that we did not get the time to do. So we are all very busy people. So when we look back, we can see that we wanted to do so many things, but the time is limited. When we are on a regular profession, the time is limited for doing other things. But then once you retire, there is more time, little more time at your disposal to do the things that you could not do in the past. So I guess that's what most people do, and most people enjoy it. So I wish a great time ahead for both Professor Charlie Kattakayam and also for Dr. Srikumar. So today in this scientific session, we have 5 speakers: Dr. Jindo Thomas, Dr. Sujin Babu, Dr. Karina Malayakal, Dr. Vaishak CP, and Dr. Ashwati Balagopal. So the first talk will be delivered by Dr. Jindo Thomas. Jindo Thomas studied in Devagiri from 1995 to 2000. He did both his pre-degree and BSc physics there, and his MSc physics was from IIT Madras. Immediately after his MSc in IIT Madras, Jindo in fact came to the Raman Research Institute, and we worked together in my lab. I had joined RRI only in 2000. So Jindo came just 2 years later in 2002. And Jindo worked with me. We worked together, I remember, in those days in the lab. And Jindo was instrumental in automating our C-scan experimental setup. So in those days, nowadays it might look a little easier, but so many years before, almost 20 years before, these were not very easy things to do. And I still remember how much Jindo struggled to find some particular commands for interfacing the oscilloscope with the stepper motor and the computer and all that. For one particular command, I still remember Jindo spent something like 2 to 3 weeks. And eventually, everything worked, and our joy had no bounds because it was a great victory for us. Later, Jindo moved to IPR Ahmedabad as a scientist, and he is now involved in developing high temperature plasma diagnostics for the tokamak plasma at IPR Ahmedabad. And I should add that Jindo is probably the first person in the country to have successfully set up a Thomson scattering setup for diagnosing the plasma parameters of the tokamak plasma at IPR. He is also actively pursuing basic research in laser matter interaction in laser plasmas. So I'm very happy to welcome Dr. Jindo Thomas for his talk here. Over to you, Jindo.
Thanks a lot, sir. Actually, I have a lot of things to be happy. First of all, giving some presentation in Devagiri College, and moreover that you are becoming the moderator of that. And as you rightly mentioned, I probably started the research career with you, and taken it forward later from RRI and working here. I'm just trying to, one second, I'm just trying to share my slides. I may start that. Is that visible to you, sir?
Yes, it is visible.
Okay.
Yeah.
Okay, so what this you are seeing the picture, actually this is a picture of Institute for Plasma Research, and today I'm talking about measuring temperature in millions of Kelvin with the lasers, and Institute for Plasma Research and aided institute under the Department of Atomic Energy, Government of India. I used to start the talk in this way, that East said that education is not the filling of a pot, but the lighting of a fire. And I believe I also got some spark from that fire lit by the teachers of Devagiri College nearly 23 years back when I joined there for my BSc and all. I still remember Professor Charlie, who was teaching us the optics and spectroscopy. And incidentally, the spectroscopy is one of the extensively used tool for basic plasma research in my lab. Richie sir is well aware about that. And plasma spectroscopy is essentially a game with optics. Charlie sir, I still have some memories of Raman spectroscopy you discussed in the class and the green color of book Banwell as well. I have very good memory of Sri Kumar sir joining the college. I think it was in 97, 98. And initially he was the physics lab in charge of my batch. I remember Dr. Sri Kumar, who is a master in dealing with the CRO. And to me, it was a stupid box with lots of knobs and full of troubles. And we always wonder that how come this person can come and do some minor touch here and there, turn few knobs, the knobs which we never looked, and get the signal. I'm thankful to Sri Kumar sir for his lab lessons as at present as an experimentalist. Rightly, Dr. Reggie also showed that one, the initial work with an oscilloscope, and I think I owe a part of that credit to Sri Kumar sir as well. Later, Sri Kumar sir introduced us to modern physics, and we are just at present, whatever the work we are just doing has got a lot of connection with the modern physics which he taught us there. I'm really happy and proud to be here as a speaker, as mentioned earlier, where two of our loving teachers are retiring. I know that this is not a very pleasant feeling for any, but certainly this is a great occasion for Charlie sir and Sri Kumar sir, as they are going to get the much the service of Charlie sir and Sri Kumar sir was in line with the motto emboldened on the emblem of Devagiri College, which says Pro Dio et Patria. That means for country and nation, for God and nation. I also wish to thank the physics department for organizing and its organizing team for providing me an opportunity to be part of this event. It is very evident the meticulous planning of the organizing team, that the seamless working of this meeting, and a special thanks to Ms. Aparna and Dr. Miril. So I'll try to share some basic information which I feel may be interesting to the audience. Now, about the institute which I am working in, the IPR, we are involved on basic and application-oriented research on plasma physics. So we have two functional tokamaks. Tokamaks is comparatively bigger scale instruments for nuclear fusion-related work or basic studies for that. And the IPR is working for the motive is energy generation from nuclear fusion in the coming future. And the two pictures what you are seeing is Aditya, which was commissioned around 20-30 years back, and SST1 around 15 years back. And still both of these tokamak are functional. And since I could see that the audience involves a lot of students,
Excuse me,
it should be mentioned. Hello?
Jindo,
Yes, sir?
I think your slides are not moving.
Oh, really? Now I am on slide 4. I think I'll just see once again on that.
Now it's moving, yes. Now it started moving. So,
okay. Maybe
yeah.
now I am on slide number 4, sir. Are you seeing that?
Yes, I can see slide number 4. Maybe you can go to slide 2 and 3 very quickly and come to slide 4.
Yeah, okay. This was slide number 2. This was code. I think we can just skip that. And slide number 3, I think now, is that visible to you, sir?
You are on 4 now. I mean, I don't know about the others, but I can see only 4.
Oh, that means that there is a lag, it seems.
What about the others?
Now
it's 3. Now it's 3.
Now it is 3. Okay.
Now it
not
is
in the presentation mode. We just
Yeah,
yes.
and now it is in presentation mode. Can you?
3 is seen now. 3 can be seen now.
Okay, I think it is going a bit slow. Now it is 4. I have changed it to 4. Can you see that?
No, it is 3.
Still it is 3.
Yes. Dr. Srikumar, maybe I think you suggested something.
No. Now it is 4. I think you can change this to slideshow mode, no?
Yeah, it
This
is actually, sir, it seems it is working a bit slow. Now I have changed it to side show, but it will take maybe a couple of seconds to be active on that.
Okay.
I'll go a bit slow on changing the slide.
Yeah.
Now I'm seeing it will slideshow number 4.
Now it is 4.
Okay, let us try. Let us see what happened later. Okay, so the opportunities in IPR, considering the large number of students, probably the BSc and MSc students. So we have opportunities as scientists and engineers. Normally after your MSc or PhD or BTech or MTech, you can just whenever there is advertisement and one should apply. And yes, the number of posts may be limited, but you should apply for that. I remember in 2004, Dr. Reggie was motivating me to apply for this one because I was reluctant because this was only one post available at that time. So I got in here. I got it here even after that. So the PhD students will be taking around 10 to 15 PhD students every year through GATE, JEST, and JRF. And in addition to that, your principal, Professor Sabu sir, he rightly mentioned about projects. We do have projects for MSc, BTech, and MTech students, which is normally for 3 to 6 months. In addition to that, nearly 2 months summer schools. I used to get students from summer school from Kerala, but for the duration of, I was the organizing member for almost 6 to 7 years, but hardly I have seen an application from Devagiri for some reason. But maybe the course schedule and all that may be difficult for them. But I have seen applications from other institutes, other colleges, and I in fact got few students from Kerala also. And in addition to all this one, we have number of collaboration for faculties through BRNS in fusion and allied area. I'm changing to slide number 5. Okay. So I said that the motto of the institute is basically fusion and its energy. A slide which is discussing about the fusion. So we'll be just considering the deuterium-tritium reaction, which is best suited for the generation of energy. And the source, the deuterium, is available in seawater. And the advantage is that tritium can be bridged from lithium-6 using the fast neutron generated in the fusion reaction itself. So, in principle, the fusion reaction itself will generate the fuel also. That's a cool idea because you just take a few gallons of seawater and go for a fusion reactor and get enormous amount of power out. Well, it is easy to say, but things are not that easy to get that fusion initiated or fusion to maintained. Let us just come about that slightly later. Now I am on slide number 6. So
we are
the
still
fusion
in slide 4, I think. Isn't it, Reggie?
Oh, still it is on slide 4.
Now it has changed. Some delay.
I think this may be something to do with the refresh rate. I will be just changing to the slideshow and back. And now it is on slide 6.
Okay.
Yes, now it is 6.
Okay, so now I got some technique that, okay, I may have to come out maybe some issues with my PC on that. So, fusion through plasma. So now plasma, all know it is, we'll be say that this is the fourth state of matter, or it is an ionized state of gas, let us say, let us not concentrate much. So the plasma contains ions, electrons and neutrals, but macroscopically it is neutral as both electrons and ions are equally balanced. Now it will remain in a state of plasma as long as sufficient energy is provided to keep it in that state, because it will recombine and it will lose its energy. So you need to continuously keep energy until you attain a fusion. Now let me go to the next slide. This is slide 7, which shows the plasma for fusion reaction, that the DT reaction is the most efficient one. But you look at the x-axis, the temperature for a DT reaction to happen, you need it in millions of Kelvin. When I am talking x-axis, I don't know, I'm not very sure that it is slide number 7. Are you seeing, sir, Raji sir?
Yeah, yes.
Okay.
We are seeing slide
So
seven.
the DT, the magnetic confinement method, that is what basically we do in a tokamak, currently hold the greater promise for generation of power from fusion. There are alternative methods are there, like stellarator or laser fusion, inertial fusion, etc. and all that. But at present, it is the magnetic confinement which may yield a result, a faster or an earlier result for a fusion, power from fusion. But the issue is that you need millions of degrees centigrade for maintaining or for getting this fusion. And for the completion, I'm just moving to slide number 8. Now, the power from fusion reactor is much like the power from any other part apart from that fusion section. So you have to have a fusion reactor, and the energy from that one would be going to a conventional power conversion system and to the grid of that. But the fusion reactor, once built, is expected to be the most complex machine ever built, because the magnetic coils which confines the plasma has to be maintained in some Kelvin, 3 to 4 Kelvin at superconducting temperature. And few meters away, the plasma core, which would be at 150 million Kelvin. So probably in the universe, not only in Earth, in the universe itself, such a kind of temperature gradient may not be present anywhere else. So the complexity, we believe that the complexity of fusion reactor going to be the highest. And because of that complexity, attaining the fusion itself is also an extremely difficult task. Now my talk was about temperature. Is that visible slide number 9?
No, it is still 8. Now it is 9.
Okay. So how do we measure such high temperature? We know that no material can withstand such high temperature. Fusion can be attained only when the plasma reaches a high temperature and density. So there is a criteria known as Lawson criteria. The temperature, the product of temperature, density and confinement time must be more than some certain value. Hence, quantifying the plasma parameters like temperature, density and confinement time is one of the important requirements for the fusion research. And the possibility of the nuclear power has already been demonstrated. There are missions, not in India, the mission like JET or D3D in Europe and America. They have demonstrated that yes, fusion power it's possible. But to get it into a commercialization, we need miles to go. So at present, and all international communities is joining their hands together to make a single mission, which is known as ITER, that is happening there in France. Now, coming to the temperature, as we all know, this may be an elementary thing which many or you are it would be well understood. But the concept of temperature is that it is the measure of hotness of the body. Now, the temperature can be determined by measuring the average speed of the body's molecules. So we can say at 300 Kelvin, the gas molecule will have a velocity of 500 meters per second. So I would say a physics student say that on a hot day, somehow the molecules are faster today instead of that itself is a measure of temperature. And this is coming from the equation half mv square is equal to 3 by 2 kBT. And the graph which I am showing, it shows that one, the distribution of velocity as the temperature increases. you can see that as the temperature increases, the distribution is also becoming broader and broader. So as at the higher temperature, this is broader and the average velocity would be increasing. So if we can measure the velocity of the or velocity distribution or the average velocity of a gas or species or an item, then we can just calculate and state about the temperature. Now, whenever we talk about the temperature or fusion, I'm coming to the slide number 11. All fusion talks is kind of an incomplete without showing a picture of sun. So I am also showing a picture of sun here. The core temperature of sun is estimated to be around 15 to 20 million Kelvin. This is only an estimate, and it's not a measured value, but yes, it is 15 to 20 million Kelvin. Whereas the outer photosphere, the temperature is somewhere around 6,000 Kelvin. The question is, how do we get these numbers? I'm just trying to get that answer, that how do we get these numbers on that? Sorry, slightly messed up. Okay. So we know the conventional methods of measuring temperatures, mechanical methods with the normal mercury thermometers, electrical methods that will be using thermocouples and RTDs in many of the research labs and places. Cryotemperatures is measured using special thermocouples. Question is, how do we measure the temperature beyond 300 degrees centigrade? So at this time of COVID, we all know that non-contact measurement with IR gun, even though that has got a laser, that this the laser has nothing to do with the temperature or temperature measurement. The IR gun collects the black body radiation of the object and it is falling to a sensor, and the electronics is displaying the temperature. And in the modern physics, you have just learned about the Wien's displacement law, that as the temperature increases, the emission from that body is shifting towards the blue region, and you can just see that kind of a distribution in the emission wavelength. This is the concept which we will be just using for the estimation of temperature. So how do they measure the temperature of the sun and stated that it is around 6,000? So I am on slide number 4, and I hope this slide is visible to you. The black body radiation, from the concept of black body radiation, the red color data or graph is basically the spectrum taken of sun at sea level. There you can see that a lot of absorption bands are there. But if you are taking the sunlight from a satellite or from above the atmosphere, then it would be seen as this yellow data. And if I am fitting a black body radiation equation for a 5778 Kelvin, then that is best suited for the emission spectrum of the sun. So hence we can just say that the sun, from where the light is coming, has got the temperature of 5778 Kelvin. But so this is the issue is that if you want to measure the sun's core, you cannot possible, because that's not emitting light for this. But we can know that sun's outer, like the photosphere, has got this much of a temperature, and the core temperature is estimated from the calculation considering the fusion reaction. Now there is issue that how do we measure the temperature? This is on slide number 15. The demonstration of using of laser for high temperature measurement has been done in way back on 68. In a international conference, the scientists from Russia claimed that they have a machine which has got temperature more than 1000 electron volt, EV. EV means that 1 EV is around 11,000 Kelvin. That they said that they have very large temperature. And the British scientists, they were not ready to believe that. And at that time, all were in a confusion that, okay, how do they know that theoretically the fusion is the way ahead, but they do not know how to get the fusion done. So the claim of Russian scientists that we have a very large temperature made the British scientists really to go up to Russia with that caricature which shows that thermometer. That thermometer is nothing but a laser-based Thomson scattering system. So at that time, at the peak of the Cold War, the British scientists named Peacock and 4 scientists, they have just gone to Russia, worked on their machine with the laser, and at that time the Ruby laser was just invented, used the Ruby laser and spectrometer, and then they indeed measure, and they said that yes, actually the temperature of this machine is in excess of 11 million Kelvin. And this was the breakthrough for the fusion research, that they all stated that, okay, this mission T3, that is the way it has to move ahead. And then onwards, the concept or the name tokamak has been underlined for the fusion research, and still we are breaking our head for the tokamak concept. So the British scientists, they accepting the Russians' invitation and working as an international collaboration, forgetting all their enemies and enmity and the Cold War, that has led into that was a major milestone for the fusion research. Now, briefly coming to the Thomson scattering. Now, the Thomson scattering, as Thomson, this is nothing to do with this has to do with the electron. This is a phenomena which is the photons are getting scattered by the charged particle. So in a plasma, we'll say that it is electron because the ions are really heavy to get affected by the laser field. So we can send a polarized light, let us say that is a laser, and this light, when it is just going and when it is meeting the electron, I have just made something which is very simple for us to understand. Let us consider 3 cases. That I'm on slide number 17. I wish everyone should see this slide. Yeah, it is visible. Okay. So a laser with a frequency omega is meeting an electron which is coming against it. And the electron which is coming with a speed meeting the electron, then the typical Doppler effect make the electrons to feel that the frequency of the laser is not omega, but it is omega plus delta omega. Now the electron will see a delta plus delta omega radiation and get accelerated in that frequency, and which emit this omega plus delta omega frequency. As I know the frequency of the laser which I am sending, if I could measure what is the frequency of the scattered radiation, I know that the delta omega, or the difference in the frequency, that is caused by the velocity of the electron. As I mentioned earlier, the velocity of the electron is nothing but it is the temperature. So this is the way we are using the laser for measuring the temperature of a plasma or any body. Now, if that electron was moving along the same speed, then the Doppler effect would act that they would be seeing omega minus delta omega. And if the electron was moving in a much higher speed, then this delta omega would be different. So the job for measuring the temperature is find out the distribution of scattered spectrum and find that how much it is getting broadened. And that broadening is nothing but that is what the temperature we are looking. So when the temperature is high, you will see a much broadened spectrum, and if the temperature is low, you will see a narrow spectrum, and then you can just put it into some equations and fit on that one, you are just going to see the temperature of that. So the advantages of laser Thomson scattering is that it is an unambiguous method, that you don't need to assume that it is a black body, or like even the IR gun, you will measure the temperature, but the people in the car also will say that, okay, you measure the temperature, the glass would be eating away all the radiation, and ultimately the guy who measuring the temperature would be measuring the temperature of your glass only, not the human. So in the laser Thomson scattering, it is unambiguous. So it's a localized measurement and can have a very high spatial resolution and time resolution, which is very important for the fusion research. Conceptually, this is very simple. You just draw an electron and a laser line and you can explain it. But the cross section is extremely low. So when I am using a 1 joule of laser energy, I am getting out only 7,000 number of photons. And 7,000 number of photon is nothing, because the daylight on your palm, it is 10 raised to 12 number of photons are falling. So from that, measuring this 7,000 number of photons is not that easy job. However, due to the accuracy and the merits, this diagnostics is worth implementation, even though it is very expensive. So the temperature which I have shown that shown as the thermometer, that will cost in India at present more than 10 crores of rupees. So this is the, and on slide number 20, this is the Thomson scattering setup for SST1, where you can see number of NDI lasers on the first floor of our experimental setup, and nearly 30 meters away, you can just see that this is a tokamak. The laser is just going and getting focused through the plasma, and at a 90 degree you are collecting the scattered photons, and optical fibers are taking these scattered photons into lab, and there in the lab your job is to find out that what is that delta omega. And for that one, and this is the real photo of the lab, you can just see here. I'm on slide number 21.
Yes, visible.
Okay. So this is the lab where you can see all the lasers and all that. Right on the right side of this photo, this is the tokamak hall, and all these 6 lasers, this is the burn patterns of the laser on a burn paper, and all these lasers are made it into such kind of a hexagonal shape, and it is sent to the tokamak through using a beam transport line, and from there you have to get back the collection of the scattered photons and get it. Now, getting that scattered photon detected, for that one you have a very less number of photons, so you cannot use a spectrometer as such. So this is basically a specially designed instrument, and we developed in-house, that multiple filters and optics and some high gain detectors, and there you are going to get a number of channels of the scattered spectrum, and from that scattered spectrum you can estimate the temperature. And this is one of the typical shot from Aditya tokamak, where I have measured the temperature. This is not a very neat curve, but the experimental physics is like this. You are not going to get, even though you wish to get a straight line, you are not going to get a straight line. So the temperature is, we do express temperature in EV. So it is somewhere around 420 EV. That means that it is a very large temperature of 5 million Kelvin. So this is what the temperature range which for a tokamak the temperature range, and our job is the existing this 5 million, we need to go to somewhere around 150 million to get the fusion to be effective. So this is what all about I'm saying. I wish to present. So thanks for your attention, and I'm extremely sorry that the presentations were with that smooth because of probably the PC issue or maybe an internet issue. I wish Charlie sir and Sri Kumar sir a great, happy, retired life. Thank you, sir.
Thank you so much, Jindo, for this excellent presentation. And now the talk is open for discussion. So any questions? Please ask now. Any questions from the audience? I have a question, Jindo.
Yes, sir.
So what is the international scenario at the moment with the ITER and also the NIF and such facilities?
The international scenario for ITER is that the assembly has been started. So actually India was the major contributor for the assembly, that the big cryostat has been delivered by India. It's a big event actually. Now that cryostat, they are just assembling that. So we do expect in another 5-year time, the ITER may get a plasma shot. And if you are getting a plasma shot with the ITER initially, maybe in another 10-year time, we would be able to say that yes, fusion is feasible as such. And then also a long way ahead for that. The long way is that one, then you need to go for a demo. And probably then India maybe also just, India is at present, India is thinking that, well, we are spending a lot for ITER. So we will get the know-how from ITER and then we may just go for a demo on that. So we can just save a lot of money on that. NIF is also just coming up good, but again, NIF issue is that this is such a short pulse as such they have to just get. So mostly the fusion community believes that the scope is there for either a tokamak or a stellarator. The stellarator W7X, that is also just showing some outstanding results and all that. And many countries, actually, in fact, China is also doing extremely well with their tokamak, HT7 and mini tokamak. And many other tokamaks are coming up, like in the West. Many scenarios people are just creating. So as such, it's a vibrant area. And only issue is the time and money. Huge money is involved. So it could be sometimes a political decision also, sometimes that, okay, where the future is going to have.
That's right. And very briefly, what's the outlook for the tokamak and IPR?
Yeah, we actually, I was busy with the coming campaign on May 5. So we are expecting, like, at present we are getting around 1 second plasma shot. And our temperature is somewhere around up to 500 to 600 EV. At present, our goal is to just increase it up to around 1 keV, and then we need to extend it.
Okay, so it can take a little more time to reach the final.
Obviously, it will. As such, the fusion power maybe another 15 years from now. And for IPR, like, in India, 15 years, maybe we may be just able to at least show something as a fusion power on this.
Yeah, I think even for NIF, they are.
Yeah, it will be. It will take time.
20,000, 2040, yes. Yeah. Okay, so thank you so much, Chinto.
Thank you, sir.
Very beautiful talk. And now I should invite Dr. Sujin Babu for the next talk. So Dr. Sujin is an associate professor at the Indian Institute of Technology, Delhi. So he did his BSc in physics during 1999-2002 from Devagiri College, and his MSc in physics was from IIT Madras, and he finished in 2004. And then he did PhD from the University du Maine, France, and finished in 2008. And thereafter, he was a postdoc for 3 years at the Institute for Theoretical Physics at the Technical University Berlin, Germany. And he taught at NIT Jaipur for about 8 years, from 2012 to 2020. And he joined as associate professor at IIT Delhi last year. And he is an awardee of the Marie Curie Early Stage Researcher Fellowship during 2005-2008. And he also had a postdoctoral fellowship from the DFG in Germany, the German Research Foundation, during 2009-2012. So Dr. Sujin Babu, his research interests are soft condensed matter, sociophysics, and biophysics very broadly. So I invite Dr. Sujin for the talk.
Thanks for the introduction. So I joined IIT Delhi actually 6 years before. So I taught in NIT Jaipur only for 1.5 years. And then
sorry. Somehow I got some wrong information. I'm sorry about that.
Okay. Thanks for inviting me for this nice event. Before I start, I have to tell that both Sri Kumar sir and Charlie sir was instrumental in me taking up physics as one of my career. I remember, two instances I can share right now itself is that during my BSc time, there was an instant during my second year when classes was not happening, and Charlie sir actually took the initiative. He took all of us to his home and he taught us electrodynamics from his home, which was, is phenomenal. As a teacher, he didn't have to do it, but he was so committed towards the students as such. And Sri Kumar sir actually taught us statistical mechanics, modern physics. And I would say that he had an uncanny knack of explaining difficult problems in very, very simple terms. I mean, I have very nice encounters with them, very funny encounters. If I have time, I will share at the end what that was. So again, I would like to thank the organizers of the meeting for inviting me, and I will start with my talk. So I hope, yes, I hope the slides are visible, right?
Yes.
Okay. So I broadly work on biophysics, soft condensed matter, and a little bit of sociophysics. Today I will be discussing about the biophysics aspect, which I work on. It's a broad area, biophysics. So the area that I am interested in is to look at how microorganisms in the sense, all the unwanted things which makes you sick, how do they actually swim? So it's only one aspect of microorganisms. There are other very nice aspects of microorganisms, but today I will basically focus on the swimming of microorganisms. So this is a picture of exactly what the starting point is and where we would like to reach at the end of maybe 50 years or so. So here you can straight away see that here you have certain microorganisms, which is basically spermatozoa, then there's an algae, Chlamydomonas, and then you have some kind of bacteria, and then all of these have these tentacles kind of thing, which is basically called a flagella. The idea is that we somehow identify or understand how the microorganism swims, and once we understand how the microorganism swims, we probably will be able to control where the microorganisms go. So the proposed way of controlling the microorganism is given here. You can either use a magnetic field, or you can use optics, light, or you can use a chemical gradient by which microorganism can swim towards a chemical gradient. And once we understand that, then we go ahead and identify these things, which are basically polymer-based compounds. You take these things attached to the microorganism, and then using these microorganisms, which can be controlled using these techniques or tricks, you can carry whatever you want. For example, if you look at here, there is a big hole here. So you can carry drugs, medicines as such, and then we can use something called the targeted drug delivery, which means that the organism will go exactly to the place where you have an ailment, you have the disease, and will apply the disease only at that particular point. And it doesn't have to go through your entire body, which helps in saving a lot of drugs as such. Plus, you have little side effects. You don't have a great side effect as such. You will have very little side effects. So these are basically the idea, the broad idea, why we should understand the microorganism swimming. The other idea being that if you are infected with some kind of disease, obviously you want a cure for that. And once you understand how the microorganism swims, you can definitely make it stop. So before we start with, so I'll basically introduce the basic ideas of this. So once we understand or we agree that we have to talk about the microorganism, one of the important parameter which comes in our discussion will be the Reynolds number. Reynolds number in very simple sense gives you, let's say, inertial forces by viscous forces. Viscous forces, you consider a viscous fluid like oil or honey. It's very difficult for you to go through a honey or a oil compared to, let's say, a swimming pool. So this number gives you, in a very broad sense, some idea of how difficult it is for you to move around in a fluid. Although the number signifies many other things. For example, if you are swimming in a pond, the Reynolds number calculation will turn out to be 10 to the power of 4. Okay, so all these parameters, rho is the density, eta is the viscosity, L is the length, and U is the velocity of the particle. So if you put all these numbers, these are simple numbers, and you know all these numbers. If you put in, you get a Reynolds number of 10 to the power 4. If you are swimming, if you are considering a fish in an aquarium, this number turns out to be something like 10 to the power of 2. And now, if you consider a microorganism of, this particular microorganism name is African trypanosome, and if you calculate the Reynolds number for this turns out to be something like 10 to the power of -4, which means that this is approximately equal to 0. So that's why it's called low Reynolds number, or you can think of it as a 0 Reynolds number system. Now, the one other factor which I didn't explain before, why we should do a study on this. This microorganism basically affects human, although it is not in our part of the world, Asia. It's more in the African subcontinent, where this organism, once it gets affected, what happens is that you get infected by a disease called sleeping sickness. And what happens is that you just sleep. You'll be standing doing something and you will suddenly sleep. Although it's a very funny disease as such, but it is fatal, which means that you will die if not treated. Now, the tricky part is that if you are getting treated with the available drugs, you can also die because the drug itself is too toxic. So if we can identify how the microorganism swims, then, by some way, we can actually try to stop it. So this is the basic motivation of, giving or understanding the swimming of microorganisms. As I work in theory, I need to introduce some kind of mathematics. Don't worry. These are all simple calculations as such. So this microorganism swims in blood, for example, or in a fluid. So the fluid equation is basically given by this, which is called the Navier-Stokes equation as such, where U is the velocity of the point, rho is against the density, P is the pressure at that particular point, eta is the viscosity. And this is basically the continuity equation, which you have studied in electrodynamics. Now, because I've said that my Reynolds number is 0 and Reynolds number is somehow defined as rho u L by eta, here you have a rho factor, you have a u factor, and then if you multiply an L divided by eta here, then this point, because the Reynolds number is already said to be 0, turns out to be 0. So the equation that you need to solve for the low Reynolds number hydrodynamics turns out to be a simple linear equation. And second, one most important part is that it is time independent. Now the question is, what happens when it is time independent? What happens when it is time independent is that you have no idea about the time. So here I'm showing an organism called a scallop. A scallop is an organism which gives you pearls, for example. So here, what happens is that the scallop is open, then it is basically closing, and then it is open. Now, because there is no time dependence, you cannot guess whether the time is moving from this side to this side or this side to this side. It is all fine. But then what happens is that if the scallop basically opens, let's say if it is open, the fluid is flowing in, so maybe the scallop moves a little bit. Now, from this point, if the scallop closes, the same amount of fluid will go out, which means that it goes back to the earlier state as well. Which means that the center of mass of the scallop will not move, which means that in low Reynolds number hydrodynamics, if the movement step is time reversible, which means if I increase the time from this side to this side, or actually I do the opposite thing, instead of putting t, if I put a minus t, if I'm not able to recognize the difference, then the swimmer or the low Reynolds number swimmer, the microorganism, they will not be able to swim. Now, so here I will try to show in terms of a simple movie. This is how the scallop will look like. So the fluid I have removed just for that you can understand or you can see the effect. So here the scallop simply is trying to move and it is not able to move at all. The center of mass remains exactly at the same point and it is not undergoing any kind of dynamics. So this is one issue which the microorganism has to take care while it actually swims. Now, another very important part is that if the time factor is not involved in the calculation, one thing which comes to our mind immediately is that the general mechanics that we have learned, which is basically the Newtonian mechanics as such. Right now I'm forgetting about all the relativistic effects and everything. So the Newtonian mechanics simply is written as F is directly or F is equal to rate of change of momentum. And the reason why you are able to do it is because you have something called the inertia. Now, if the time dependence as such is not there, then your system is itself without inertia. Remember, I just told that Reynolds number is something like inertial forces divided by the viscous forces. So there is no there is no inertia in the system. Now, because there is no inertia in the system, you have two problems. One problem is that the moment you stop your propulsive mechanism, whatever that may be, it might be a simple tail which swings, or the head doing kind of a helical wave as such. But the moment you stop that, the motion will be stopped. And which means that the microorganism themselves has to keep on beating if it wants to move. So it's a very harsh environment as such. It needs a lot of energy to do that. So unless the microorganism is ready to beat all the time, it will not move. Now, because there is no inertia, I cannot write force is directly proportional to acceleration, considering m is a constant here. What we write in that case is basically, instead of the Newtonian mechanics, we comes to the Aristotelian mechanics, which says that F is directly proportional to the velocity. And remember, this is not something new that I have just introduced. You have already done it in terms of fluid dynamics in maybe, in your mechanics course, where you have written F is directly, or F is equal to 6 pi eta AV, where V is the terminal velocity. When a sphere falls through a fluid of viscosity eta, then the force exerted by the sphere as such is simply given by 6 pi eta AV. This is the well-known equation that we keep on doing. So once we have introduced the idea of force and we said that force is directly proportional to velocity, and remember the velocity, although we are saying force is directly proportional to velocity, dimensionally everything is right because the viscosity and the radius term will take care of the dimensionality. So here this equation is simply rewritten in terms of a constant psi here, and psi is simply given by 6 pi eta AV. So what this says is that if you put the sphere in a viscosity, in a fluid of particular viscosity, and you push it, you need a particular force F to move it with the velocity V. Now, if you increase the viscosity, it will be even harder for you to push, or you need more force to push the sphere through the fluid. So this eta is, in fluid dynamics term, is simply called the friction coefficient. It basically acts opposite to the direction that you apply the force. That's basically it. Now, for a sphere, it doesn't matter in which direction you are pushing, because it is isotropic in every single direction. It doesn't matter. So your eta remains the same. The friction, the difficulty by which you can push the sphere in every single direction remains the same. Now, if we come to the second part, which is, instead of a sphere, if I now consider a rectangle. You see, if I want to push the fluid, or if I want to push a rectangle in this particular direction, it is very difficult for us to push, because the area that is going to be in contact with the in contact with the fluid is much higher. So it will be very difficult for us to push in this direction compared to this direction, because the area here is only this much, which means that the friction coefficient now along the perpendicular direction and along the parallel direction, so perpendicular with respect to the axis of the cylinder. So you need two kind of forces. So it will be very difficult for you to push it up like this, and very difficult for you, or easier for you to push it in this particular direction. Now the microorganism utilizes this particular idea for it to swim. How do you do that? So here I have shown the picture of a microorganism, which is spermatozoa, and the flagella, which is this particular region. You have extended this, or zoomed into a very small quantity, and this is basically the zoomed parameter. So here also I have used exact same concept which we have learned in your Newtonian mechanics, if you want, that you can take a force and then you can resolve it into parallel and perpendicular component. So here you have the velocity in one particular direction, and which is resolved into the parallel and perpendicular direction. The force is in this direction. Again, it has been resolved into the parallel and perpendicular component. And if you write down by solving this, balancing the forces as such, what you will get as an equation is simply this. So if you have a sphere, you know that epsilon perpendicular and epsilon parallel are the same, so the propulsive force becomes 0. But if you have a cylinder as such, the propulsive force is, although a very, very minute quantity, which is basically given here, very, very minute quantity, but a force do exist in our case. Now, because of this force, the microorganism is going to swim through the fluid as such. And in case somebody is wondering what is the dimension, or sorry, what is the approximate number of the force as such, the force that is being generated by a microorganism is in the range of piconewtons. So it is something like 10 to the power of minus 12 newtons. That is the tiny amount of force that is being developed by a microorganism. Although direct measurement of these forces are not easy, there are some simple measurements by which, or simple methods by which we can do it. Now, the one unambiguous thing that is existing in all this work is that we know how what are the simple physics by which the microorganism moves. We know that what the microorganism uses, which is in the earlier slide which I've said, which is the drag-based anisotropy. In this slide, what we are interested in is to understand in which direction the microorganism will move. The reason which I am saying like this is because if you have a head and a tail, everybody will simply say that the direction of movement is simply towards the head. Now, it is for a microorganism, it is not a very obvious thing. For example, we are ingrained with the idea that you always move with the head forward because we know dogs, cats, mouse, all these animals, actually the head moves forward and the tail follows. Now, in case of microorganism, what happens is, again, we use the simple idea of Newtonian mechanics to understand this particular concept. What happens is that you have a wave. So this is basically the wave that I've depicted. And as time goes on, the wave travels from, let's say, from your left to your right. So basically the direction of the wave is going to be along this direction, which means that the fluid, which is around here and around here, is going to be pushed in this particular direction. The Newton's third law says that if for every action there is an equal and opposite force, which means that if the fluid is pushed in this particular direction, the fluid is going to push the microorganism in this particular direction. So if you have a head and your wave is traveling along this direction, then only the microorganism is going to move in this direction. Otherwise, what happens is that the microorganism, if the direction is opposite, like if the wave is passing from the tail to the head as such, it will move in the opposite direction. There are microorganisms which uses both these strategies to get around or to get over the harsh environment as such. Having said that, because I've said that you have a scallop, and then the scallop theorem says that if you have the time reversible motion, your microswimmer will not move at all. And the good thing about physics is that you always have all this theory as such, and then you come up with the idea that, see, it all works for some set of system, but it will not work for some other set of system. So here I'm using the exact same scallop as before. The only difference from the earlier movie that I've shown is that here, for example, the scallop is having a very flexible arm. So instead of a rigid arm, which I showed in the earlier slide, here we have a very flexible arm. And when you have a very flexible arm, immediately you will see that the scallop, which was starting from somewhere around this point, has already reached. And as we move along with time, we will see that the scallop can move in one particular direction for a longer time as such. So what is the difference? So here, this is the scallop that I have already shown you, which is the scallop which was not moving. In this, when it is closing in this particular direction, it is closing as a V and it is opening as a V. Here, if you look carefully along this, it is closing like a V, for example, but when it opens, so along this direction, it opens as a U. So if we now do, so this is if the time is like this, and now if I put a minus t, so here, if I put a minus t, the V will be closed, it is opening as a V. Here, if I do a minus t, what I see is that it is closing like a U and opening like a V, which means that the idea of time reversibility is broken in our case. and we are able to actually design a swimmer which will propel itself because the time reversibility idea is broken in our particular case. So this is basically this is the simple basic idea by which how the swimmer swims in a very harsh environment. There are many other things, very interesting things as such. Study. So the artificial swimmers, these are not natural swimmers which I've shown you, these are artificial swimmers. We put forward the idea of the scallop swimmer as such. The idea is that you have this scallop swimmer and then you will attach some kind of a polymeric compound to it, and this polymeric compound can carry enough amount of drugs, so it will go wherever it wants, and then it will attack whatever the ailment is. So that is the idea. So that is why it is called a micro robot as such. At some point, maybe in 15 to 20 years, I'm sure that you will get this kind of capsule for you, where it is completely targeted, and you basically take the pill, and then some kind of a artificial micro robot will travel through your blood, and it will affect only the region which has the problem. So a more ambitious project or a more ambitious idea is that one day we will be able to design doctors as such. So taking this very simple example, you can attach a scissors to this guy, and you can attach this can be considered as a hand. So this will go to, for example, if you have something like a hernia, this will go to your correct place and it will cut out your hernia. And it will cut out into very, very small pieces. Although you have to send millions of these micro robots there, but it will cut out small portions of your hernia. And the dream idea would be after about 40-50 years, you will just swallow a pill. If you have a hernia, you will swallow a pill. You will lie down on your bed for 2-3 hours in your home, and then after that you go to work because everything is done. And one other reason why we try to understand this is to actually stop a lot of disease-causing bacteria or viruses as such. How do we can stop them? We can understand them, and of course, the reason why we all are involved in it is to understand fundamentally how the microorganisms can utilize the very harsh environment that it is living in, and take it forward and produce the kind of technology that one day would revolutionize the entire medical field as such. So having said that, I would thank all of the participants for listening to my talk, and thank again the organizer for letting me speak.
Thanks a lot, Dr. Sujin, for an excellent presentation. A lot of futuristic implications, no doubt. Questions from the audience? Any questions?
Good afternoon, sir.
Yes.
Sir, I'm a first year MSc student, Devagiri College, and I would like to know how we would exactly determine the place where the micro robot should attack, and how we would get how you told that it would be a future, like we would exactly cut the example you told, we would cut hernia into millions of pieces, like how you
how do you take it out of the body?
Do that?
Sorry, okay. The last part of the question I was not able to get.
And how we would exactly determine the place?
Okay, exactly determining place, it's still a place of active research as such. But there are certain, let's say, enzymes which is produced in certain part of the body. So if you use the idea of a chemical gradient as such, the microorganism will start looking for this enzyme. and it will only go to the place where that enzyme is produced, or you can put a marker. This is place where I'm going to call it as India. Like that, you basically put a marker inside your body, a chemical kind of thing, and then the microorganism or the micro robot as such is going to search for that. And unless and until it reaches that, and only if the marker is of a specific concentration, it will erupt or it will burst out. Otherwise, it will keep on moving inside your body. And the other way of how to take it out of your body, it's the usual way of, if you eat junk food, how does the body cleans your stomach? Same way. It will just take it out.
Okay, thank
so
you.
Hi Sujin, Jindo here.
Hi.
So how do you see that this research for this will it be going to be replacing the chemotherapy and all that one?
Yes, that is our dream project. If possible, if we are able to do that, a lot of issues will get solved, especially the kind of cancer which Steve Jobs had, where it was impossible for the doctors to actually go in with their highly sophisticated instruments because you cannot get in there. So in that places, these microorganisms can very easily go in and just take out exactly what they should be taking it out. And in chemotherapy as well, because the issue of chemotherapy is that you get a lot of side effects because your entire body is affected because of chemotherapy. Now it will be only affecting the cancer cells and nothing else.
Thank you.
Thank you, Dr. Sujin. So let us now move on to the next talk. The next talk is by Dr. Karina Bimaliakal. Dr. Karina is at the moment a researcher at the Lund University in Sweden. She had her BSc from St. Joseph's College and then MSc from the University of Hyderabad. And she did her PhD in physics, finished in 2017 from the Tata Institute of Fundamental Research, Mumbai. And I'm very glad to say that she is a first rank holder for both MSc and BSc. And she has been awarded a research grant from the Royal Physiographic Society of Lund in 2019 during her postdoctoral research. And she was a summer research fellow of the Indian Academy of Sciences in 2009 when she was doing her master's. Her research interests are in nanomaterials and transmission electron microscopy. Right now, she is a researcher at Lund, and up to August 2019, she was a postdoctoral fellow at the same university. And for a short while in 2017, she was also a visiting fellow at TAFR. Dr. Karina.
Yeah, thanks, Professor Reggie Philip, for the introduction. I have a couple of questions before I start. One is, we're probably running a bit behind schedule. So do you want me to sort of skip a few things or try to shorten it?
If you can finish in 15 minutes, it's okay. Otherwise, you can take 20 minutes.
Okay, I'll try. Yeah. So as Professor Reggie Philip said, I'm basically doing my research in with the TEM on nanotechnology based things, which I'll talk to you in a while, actually shortly. But I have to interact with a lot of different people and from different countries, and sometimes I feel that nanotechnology is not a field that it's a field that I don't have a lot of in-depth knowledge, because they have a lot of training in nanotechnology itself, while my training is in physics. But there are so many things where I feel that just because I learned physics and because I've got my basics sort of correct, it sort of gives me a privilege in some sense. And of course, the basics in physics, at least for us, is mostly laid in our BSc time. And so I owe a lot of gratitude to all my teachers from the Devagiri College for training me in my bachelor's, and especially Srikumar sir and Charlie sir, and I wish them a great, I don't know like if they are like planning to take up a job, but I wish them a great life ahead. And we like, since we know them like in person, we know that they are so energetic that they are not going to sit at home idle. They'll do like excellent work in the coming future. Okay, now I'll come to like my talk, and are you seeing my screen? Are you seeing the first slide of my talk?
It's coming. Yes.
Okay.
Maybe you can just try going to the second or third slide and see whether it works. It moves.
So what are you seeing like right now? I guess actually like I'm using only like one screen, so you should be seeing like the one slide only.
Mm-hmm.
Yeah.
Okay.
Are you not? Are you seeing my title slide now?
Yes. Yes.
Yeah, that's fine. That's fine. Yeah. So I'll basically talk to you about like watching semiconductor nanowires like grow using a TEM, and I will talk you through like semiconductors, and I'll talk you through nanowires before going into like things related to my specific research. So semiconductor devices basically are like, you see a lot of semiconductor devices every day in our everyday lives in like terms of like electronics, our phones, laptops, solar cells, and so many of it, and majority of it are made with silicon. Silicon, as you know, is indirect band semiconductor, which means that it's difficult to get light out of a silicon device. However, if you are trying, so silicon and like even germanium for that matter, they are both group 4 semiconductors. Both of them have indirect band gap, and like applications of light emission. If you want to make an LED, you can't make an LED. I mean, you cannot make an efficient LED with silicon or germanium because they are indirect band gap materials. However, you can try to grow compound nanowires, for example, of by combining a group 3 material with a group 5 material. You can grow compound semiconductors, and many of those at least will they have a direct band gap and can be used for light emitting or light detection applications as well. And like a few other advantages are also there for specific systems in terms of like say an increase in electron mobility and so on. So here are like a few applications of like having compound semiconductors. Like I said, you can use it for LEDs, lasers, and like detectors and so on. And as you know, nowadays, like the devices in the electronic devices that we are using are actually the computer chips, and like a lot of processing which like is happening. People are trying to like make the processors smaller and smaller, as much small as possible. And currently we are actually limited by like how small we can go. How to break this and make devices more smaller, which would mean that the device itself is smaller and like lighter, or it can also mean that if you are given a particular area for the device, then you can like have more number of devices and hence like more calculation speed and like so on. And so it is important to like use semiconductors nanotechnology in like the coming days. So what are nanowires? Nanowires are one-dimensional structures. They're basically like long wires where the diameter of the nanowire is typically a few tens or hundreds of nanometers, and it's usually a couple of like micrometers long. Nanometer, as you remember, I guess you know that it's like 10 to the power minus 9. It's so tiny. So how do we why do we like use nanowires, or why are nanowires very interesting? This slide is something which I can sort of like rush through fast. So basically, one very interesting property of nanowires is that there are certain materials which grow in a particular crystal structure when you're trying to grow as a bulk piece. However, when you're trying to grow as nanowires, the energetic slightly changes, and you can try to grow in a different crystal structure also by controlling the parameters. So you can change from one crystal structure. For the example I'm showing here, it's a gallium arsenide material, or like most 3,5s actually, most arsenides and phosphides actually. It grows in zinc blende structure, but you can tune the crystal to grow in a different like crystal structure, which is like woodside in this example. Which also means that you can try to like make a lot of different like heterostructures with the same material, but you can have two different structures, and both these different structures have also different properties. So you can do a lot of gambling with these sort of structures. You can also try to easily integrate 3,5 materials on silicon, which is a very hot topic of research, but if you are trying to grow it or do it on thin films, which is a conventional way, it is very difficult. But it is so much easier to do it with nanowires, because in nanowires, the contact region between the substrate and what material you're growing is very small. Because of that, lattice mismatch between the two different materials you're trying to grow is not so big a deal. Okay, so, and like you obviously know that because they are nanostructures, it has a large surface to volume ratio. You can also try to grow different like structures for different applications, in terms of like you can have different materials along the either along the length of the wire or along a shell. Basically, it's like you can have a nanowire and you can have it coated with another material, again coated with another material, or like different structures that you can like think about. Okay, now since we know that nanowires are very, very tiny, how can we see these nanowires? Because well, when we are using an electronics, if it has nanowires or not, we don't care, because we don't have to see it at that time. But when we are like trying to optimize things, and when we are synthesizing nanowires, we want to see how it has come out, and so we try to like, we have to like see the nanowires literally. How can we like see the nanowires? Can we use optical microscope for seeing the nanowires? So the answer is that it's a bit challenging like to do with optical microscope. So you would remember from like your classes from like some time ago maybe, or maybe like even like what if you're students, you might like have a very fresh memory of all these things. So you know that if you're using any light, for example, and if you're using it to resolve like two objects, the resolution limit that you can get is roughly around half of the wavelength of what wavelength material your wavelength wave you're using. So for example, you know that the visible light is varying between around 400 to 700 nanometers in like wavelength, which would mean that if, say, take the best case scenario, it would be a 400 nanometer wavelength blue light. If you're using that, your resolution limit would be around 200 nanometers roughly. Now if you're trying to look at a 100 nanometer or a 50 nanometer material, that thickness itself is only 50 or 100 nanometer, and if you're using a tool which gives you a resolution of 200 nanometer, that means that if your nanowire is sort of going to be just like blurred, you won't be able to see any features of that wire. So this might not suffice. So what is the other option? Another option people use is called an electron microscope. So electron microscope is basically so like if you look at how things evolved over the years, basically in 1925, Louis D. Broglie suggested or theorized that electrons had a wave-like characteristic, and so this wave particle so this wave nature of moving particles is what is used in an electron microscope. So basically have electrons which are accelerated through a potential difference, which means that it's, and while they are moving, they have a de Broglie wavelength associated, and that wavelength is going to be very, very, very small. So typically in an electron microscope, the wavelength would be like maybe like 4 picometer or so, like if you're using a transmission microscope, which I'll like come to. So basically the point is that instead of using light, you can use electron as the wave itself, and look at materials with the electrons. So there are mainly two types of electron microscopes. One is a scanning electron microscope, which basically means that there are electrons falling on a sample, and it's how the electrons scattered from the sample which decides what image you are getting. Okay, that is like a nanowire, picture of a nanowire taken with a SEM or a scanning electron microscope. So here, this is like the same nanowire but taken with a different, like this is like taken with a transmission electron microscope, and you see a lot of features which you could not see in this SEM image or scanning electron microscope image. You can already see inside this TEM image. This is basically a picture which I just blew like bigger so that you can see easily. It's not really a different image. And you can actually zoom in even further. You can magnify it even further. For example, I'm just showing you a TEM picture, a transmission electron microscope picture of a nanowire. So in transmission, basically what is happening is that you're having a sample, an electron beam is falling on the sample, and whatever electrons are being transmitted from the back of the sample is what you're recording. So basically you see these like dot sort of like things. And like you see like the black portions in between, it's basically the atomic columns that you're seeing. So like you can resolve with an electron microscope even to a level of a few atoms. It's actually a whole column of atoms. It's like through the entire depth of that sample, you're having atoms sitting, but you're looking at it in a nice crystallographic direction that all the atoms are sitting one behind the other, which is why you don't see a blur, but you actually see sort of atomic columns in this picture. Okay, so now how can we like grow nanowires? Nanowires are usually grown by something called a vapor liquid solid mechanism. It means that whatever you are trying to like, according to what material you are trying to make, you supply the precursors in a vapor phase, okay? And you use a liquid catalyst. And this liquid catalyst is a nanoparticle, and you use this liquid catalyst for absorbing materials from the vapor. Now inside the liquid it dissolves. Once after dissolving like a lot of material, once it supersaturates, it sort of precipitates out as a solid. So there is like vapor coming in. It's like mixing in the liquid, and on supersaturating, it's precipitating a solid. So what happens is like there's like one layer of solid which precipitates, and then again there is vapor coming again, it's dissolving again, it's supersaturating, again it's like depositing as a solid. Okay, that's how like the VLS mechanism happens. So basically this nanoparticle and the dimension of the nanoparticle determines what dimension of nanowire you want in some sense. So let us look at an example using, if we are trying to say, for example, use gallium or grow gallium arsenide. Okay, so we want a gallium precursor and an arsenic precursor. Precursor just means that you're using a compound which, if given the ideal conditions, would decompose and give you what elements you want. So you use a gallium precursor and an arsenic precursor, and you try to like grow. Like you supply them in the vapor phase, they dissolve in a liquid. Usually we use a gold based liquid, so if it's actually, I'll come to it, and we try to like put in sufficient temperature, and then we can like cook up gallium arsenide. So usually when people are trying to grow nanowires, they use an industrial system called like one kind of system is called a metal organic chemical vapor deposition system. Don't you don't have to like give much attention to the system, but what you have to like take away is that usually you start with a substrate, you put these catalyst particles, you put the sample into a closed system, okay? And then you tell, okay, what flows you want for your gallium precursor and what flows you want for the arsenic precursor. So in like this example, I'm continuing with gallium arsenide, but you can like, it can be any nanowire, or it can be any compound for that matter, okay? and then you apply heat. And like at the end of the recipe, you can, after cooling down, you can take out the nanowire sample, and it would have like, well, if your parameters were correct, then you would have a nanowire at the end of it. So you are initially starting with a substrate and ending with a nanowire. That is good, and it can be used for a lot of technological applications. But the issue is that what is happening inside the machine is not something which you are able to see, which means that it's difficult to get an understanding about how these things are growing. So I explained that it's growing using the VLS, or vapor liquid solid mechanism. Liquid solid mechanism, but there are still a lot of open questions. And if you want to control the nanowire structure in a way that you can use it for technological applications, you need a very good understanding of how things are growing. So how can we understand how nanowires are growing is the next question I want to address. One way of doing that is to use an electron microscope to grow these nanowires. So as I showed you before, we can look at nanowires which have been grown somewhere inside the TEM and see atomic resolution things, but we want to see while it's happening. So for that, we use an environmental TEM. Basically, it's just like a specialized TEM, okay? Where you use some sort of gas handling system, basically to give what precursors you want at whatever flow you are asking it to, and you are looking at it, and you are trying to grow it inside a microscope. This is the microscope that I'm using here. So it's basically the thing inside the box, and because it's in a box, I thought I'll just take a show you a picture of how it looked like before the box was put in. So basically, this is an image with the electron microscope is just being assembled here. It's not actually fully done, but you see that it's a rather complicated system. Okay, now let's we look at it by using we use a computer screen, and we see what is happening. And what we do is we capture videos of what is happening. So we try to grow the nanowire inside the TM. We capture a video while it's happening, and then we analyze the video later to study some things. Or you can do some studies directly while it's growing itself. I'll show you few examples of what we have observed. I mean a few examples just to demonstrate that we can see nanowires growing while it's actually happening. Okay, and you see, so this is a 5 nanometer scale bar, which means that you're looking at a very, very small particle. So if you're trying to do this in an optical microscope, you can't get this sort of resolution in an optical microscope. You have to do it in a TEM, and it's rather complicated actually. Well, I wouldn't say it is complicated, but I would say it's technologically very cutting edge. Okay, so now let us look at the starting of a growth is what I'm going to show you. What you see here on the left end is a gold gallium mixture, and we are again growing gallium arsenide nanowires. We are putting a gallium precursor in and an arsenic precursor in, and trying to see what will happen. Now let us see. Yeah. So you see, something has started here, and it has started to grow a nanowire from that particle, and you can see while it's happening. So if you can see what is happening, you can get a better picture of, or better understanding of how things are happening, so that you can control it better. I'll show you another example. So this is an example where you can actually see the two different crystal structures. So you see over here at the bottom of it, you will see that it's in one crystal structure, but in the in between, this region is basically a Zinglin structure. This is a Woodside structure. You'll see a little bit better when I show you the video. Yeah. So again, we are seeing that the nanowire is growing, and you are seeing layers growing one after the other. Yeah, so basically you are able to change the crystal structure. You are able to get and when you like do that, you can understand a lot more about what determines these crystal structures, how you can change it, and so on. Another advantage of using like in situ methods is in that sometimes when you have messed up an experiment, you can sort of like regain it or like correct it. So actually in the example that I'm showing you, we had unintentionally increased the temperature a bit too high. Actually, like we increased the temperature and realized that it was not a great idea, and I'll show you what happened. So this is a particle, this is a nanowire segment that you see on the left side. Okay, let us see the video now. Yeah, so what happened is basically that it started eating the like nanowire, but we didn't want that. So like we decreased the temperature again and it started like putting the nanowire back again. Yeah. So like that actually is not really a like great research, and I would say just like a fun thing to show you. Okay, now let me like show you a couple of results from like the work I'm doing here. Was basically, so actually growing nanowires inside a TEM is has been like demonstrated by people earlier also, and there are like I think maybe like 5 or 6 groups which study nanowire growth inside TEM all around. Like 5, 6 would be like total world, but like what we are doing is not really like that's like what topic we are doing is, or the growth of nanowires inside the TEM is not something is specific to our group. But like I'll show you a couple of research which was like done in our group, which people had not studied before. So here the first example is where we are trying to measure the catalyst composition while a nanowire is growing. So what I'm having is a gallium arsenide nanowire. There's a gold particle based catalyst. So you started with a gold nanoparticle, which is a solid when we started, and then we like increased to a reasonably high temperature and we introduced the gallium precursor and the arsenic precursor. What happens is that some of them like mixes with the gold and then like becomes a liquid. Now the catalyst composition of this nanowire is very important, because like the composition becomes a lot about like the chemical potential, and like a lot of theoretical simulations can be done like when you know the catalyst composition. However, people did not know what the catalyst composition was during the growth. So people did not have that provision before. What they would do is they would grow the wire without seeing it. Then they would cool down the wire, take it out of the industrial system that I showed you, and then measure it. But when during the growth, it can be very, very different from like after the growth, because growth is happening when there is a gallium precursor, arsenic precursor, and at a high temperature. But it's very different. Like once you've cooled down, the system is totally different, and you can't understand what the catalyst composition was during growth by doing a ex situ or like a later on like research. So what we did was like we studied for the first time the catalyst composition in situ, like while the wire is growing, and in the same instrument that it's like happening, we studied the catalyst composition, and we saw that there is a lot of ignore the silicon peak. It is basically it's basically the substrate. And there's a lot of gallium mixed inside the gold, but there's actually very, very little arsenic dissolved inside this catalyst particle. So this is an interesting observation. I won't say it's sort of expected, but people couldn't like measure it and like show that that is the case. That's it. Okay. Another research I would like to show you is basically where we are trying to like grow nanowires, and as like you might have seen in previous videos, you are like having the nanowire growth layer by layer, and what we did is to like try to study what determines these layer growth, what starts a layer, how can we control how long it takes for each layer to complete, and so on. And this is like a nice study where we also saw that the layer growth is not an instantaneous process. That's interesting because most people or most theoretical papers assume that it's an instantaneous process, but we see that it's not the case. So that is all what I want to tell you today, and thank you all for your attention, and thank you again to Srikumar sir and Charlie sir for their excellent teaching and their motivation to pursue physics or material science. Actually, I'm doing material science, not exactly physics, but to continue in science. Thank you and best wishes to them. Yeah.
Thanks a lot, Dr. Karina, for that excellent presentation. Questions from the audience? Students? So I have a small question to you. So what's the best resolution you have with your systems at the moment? I mean,
So what we have, the resolution we have at the microscope I'm using is 0.8 angstrom.
Mm-hmm.
So 0.08 nanometer is what we are having. Yeah.
Must be a very good system then.
Yeah. Okay. So it's actually a TEM with it has a aberration correction. So it's basically there's a conventional TEM, and usually when people if you look at optical microscope, the optical microscope which are available now is very close. You can have microscopes which are near to the resolution limit. I mean, there are very advanced optical microscopes. Right, but in TEM, if you look, actually you might know. I thought maybe students also it will be good to say. So electron microscopes are in some sense it's in its infancy. So the resolution which ideally you can get with a TEM should be as good as 4 picometer, which is much smaller than what we are having. But the problem is that the instrumentation is so difficult, and people sometimes say that what we are using now, even with the so-called advanced TEMs, is you can compare it with if you were using the bottom of a Coca-Cola a bottle. If you fill some water and if you look at a leaf or any your hand or any specimen, that magnification, it's as bad as that what we have. So there's a lot of scope in electron microscopy and instrumentation which can go ahead. Yeah, but the current technology would be it's sub-angstrom resolution, which most people have currently in good microscopes. So what we are actually having is we have this Coca-Cola sort of microscope, and because there are a lot of issues, there is additional system to sort of, we know this much is the issue, so let us try to I mean, you put a lot of you introduce some extra twisting and bending in order to make it slightly good, and that is how that's how aberration correction is called, and that's how we can get at least sub angstrom. But yeah, this is far away, far poorer than the resolution limit achievable. Yeah.
It's very good to know that.
Yeah.
Yeah. Thank you.
Hi, Dr. Karina.
Yeah.
This is Vaishak here. Was a wonderful presentation. I just have a small question, because is the TEM limited by the thickness of the sample you're measuring?
Yes. Yeah. So so I won't say it's that technique is sort of limited by what thickness you have. So then if I grow say 100 nanometer or a 150 nanometer nanowire inside the TEM, basically the image will be just as good as an SEM. You won't see atomic lattices, you won't be able to get any resolution. So usually the thickness of the sample has to be roughly in the order of 50 nanometer or smaller. So if you're having something in 5 nanometer, 10 nanometer regime, that will give you great results. But that might, so in my case, actually, I don't know if you noticed, so when I was showing the layer by layer growth, we actually had to use a slightly fat nanowire, because what happens is when it's a very, very tiny particle, the growth mechanism actually is determined, like a lot of energy balance gets changed because of the size. When it's too small, it's like I mean, even in nanotechnology senses, very tiny like particles, if you go like 1 to nanometer particles, it's a totally different like energy balance there. So you won't be able to compare it with the real space thing. So like some of the pictures that I showed you, which are sort of like not the best pictures, because we had to like use a reasonably wide material so that it can be compared with what people would use in outside the TEM for any application or for studying any application based things. Yeah. So it is limited by like thickness of the sample is a major limitation. Yeah. By the way, like in a TEM, by using the TEM, sometimes people actually can look at it in the scattering mode also. So though you are using a transmission electron beam, like a microscope, your spot size is going to be much smaller than an SEM, but you can look at the scattered beam instead of the transmitted beam. So you can do a SEM inside a TEM instrument in some sense, and that will give you a better resolution than an SEM done in an SEM instrument. But you won't be able to get atomic resolution if it is like thick sample. You will only get the surface features.
Okay.
Yeah.
So the reason I asked is, it's possible that if you grow it on such tiny, are you limited by the thickness of the substrate too? I'm guessing yes.
So nice question, very nice question. So what
could it
we
be
are doing?
used? Yeah, the motivation of this question is to know if you can really use these samples, or are these just to learn the dynamics that's taking place there.
Yeah, so 2 questions. The second question, yes, we are basically trying to look at the dynamics. So the nanowires which we grow inside the TEM, we don't use it for any application or anything. It is like what we are doing in our group is basically to understand how the wires are growing, but like we don't use these nanowires for any application per se.
Okay.
The question you asked before that is whether the substrate thickness is an issue. So like, so substrate thickness, if there was a substrate, that will be an issue. What we do for that is basically we have a substrate with holes. Okay. So like hole essentially is main, like at least locally you don't have a substrate. So you basically have like, if this is a nanowire, and like you are looking at the whole region, so it's basically limited by the nanowire thickness and there's no substrate below it.
Okay.
But very nice question. And actually in TEM, most of the time you can like commercial like chips for like TEM characterization also, you can like get where there is a mesh of like copper. On that there is a film with a lot of holes. So when you put the sample, you can like you're still limited by the thickness of your the like particles or nanowires or whatever you're trying to look, but you can have locally you can have a substrate free region if you want to look. Yeah.
Okay, that's cool.
Yeah.
Thank you.
Thanks, Vaishak.
Thank you.
Okay, very nice. So thank you very much. So now I guess we can move on to the next talk by Dr. Vaishak, CP. So Vaishak is right now a postdoc at the Department of Dielectrics, Institute of Physics of the Czech Academy of Sciences. And he did his BSc in physics in 2012 from St.Joseph's College. And his MSc was in 2014 and PhD in 2019, both from ISER, Trivandrum. And he worked on Terahertz spectroscopy, I guess, Terahertz properties of 3-5 Bismuth semiconductors. And Dr. Vaishak's current research interests are Terahertz spectroscopy, Terahertz scanning near-field optical microscopy, transport in inhomogeneous media, and non-destructive analysis. Dr. Vaishak.
Thank you, Professor Raji, for a kind introduction.
Welcome.
So Is the slide visible to everyone?
Yes, it is visible.
Okay.
It's a second slide. Not
Yes, that's the second slide.
Yes.
Just a second. I'm sorry about this hiccup. Yeah, am I now in the presentation mode?
Yes, we can
Yes.
see your slide.
No, not in the presentation mode, but
Okay. What about now? Now?
now in presentation mode.
It's in the presentation mode. And I hope it's just the presentation slide you're seeing, not my notes.
This is second slide.
Yes, just the slide and no notes, I hope.
No notes.
Okay, thank you. So, good afternoon, everyone. I'm Vaishak, and it's an absolute pleasure to be part of this event. And it's an absolute honor. It's an absolute honor to be having given this opportunity to speak at this occasion. And we know that our, excuse me. Okay. So as I said, Srikumar sir and Charlie sir, as we all know, are the two strong pillars of the department and the college. Excellent teachers, both of them. They have helped our batch in many occasions with our batch tour, with our science fest, and lot more. I could take up the entire time talking about it, but due to the lack of time, let me just take this opportunity to thank both of you on behalf of batch 2009-12 for the support and inspiration. And I'm sure that both of you will be missed at Devagiri. We already miss you. And now let me move on to my presentation. I'm going to talk today about Terahertz Spectroscopy. This is something which I have been working on for the past 6 to 7 years. The idea of this talk is just to give you a very brief introduction of the terahertz science and a brief introduction to how instrumental femtosecond lasers are in the generation of terahertz radiation. So, terahertz radiation is, you know that microwave and infrared spectral regions are two of the most thoroughly studied areas of electromagnetic spectrum. They form the electronic and photonic branch of optics, if you will. And right between these two giants, we have a spectral region called the terahertz spectrum, which is characterized by frequencies in the range 0.1 to 10 terahertz and energies in the range 0.4 to 40 millielectron volt. Unlike its neighbors, terahertz spectrum is far less understood. You can, by just thinking about the telecommunication network and the system we have today, you can imagine the extent of impact the microwave and the NIR spectrum have on our life. But compared to that, terahertz spectrum is a bit of a mystery. At least it was 30 years ago, and we called it the terahertz gap. The entire universe is a source of terahertz in one sense, terahertz radiation in one sense, because the cosmic background radiation peaks around 0.2 terahertz. So for the temperature, if you plot the black body spectrum at 2.725 Kelvin, you would see that the peak appears here around 0.2 2 terahertz. And a lot of black body radiation which we have around has terahertz components. But these are too weak, and these are unusable for any spectroscopic applications. These are not strong enough in any sense. They are almost, buried in, orders of magnitude higher noise. And it is a bit ironic to call it a terahertz gap. It's a gap not because there is no terahertz radiation around, but the gap arises because we as human beings were not able to create any measurable or reliable amount of terahertz radiation or neither detect it. And yes, and so even until late 80s, this spectral region was considered the final frontier of electromagnetic spectrum, because so many of the technologies or techniques and formalisms of microwave region or infrared region applies to terahertz region. It's in between, and it's neither here nor there kind of a situation. But we started filling the terahertz gap early in the past few decades, and many of the earlier sources were continuous wave sources, and the efforts were made by scientists to really reach the terahertz spectrum from the microwave and also the infrared ends. But this scene started to change rapidly after the inception of ultra-fast or femtosecond lasers. Today, there are tabletop sources that can cover entire terahertz spectrum. Half of my talk is going to focus on how the femtosecond lasers brought about this revolution in terahertz science. And of course, the scientists did do that by standing on the shoulders of giants like Clerk Maxwell and Heinrich Hertz, two of the giants of electrodynamics. And the classical electrodynamics explains how radiation emerges due to accelerating or oscillating charges. So in these equations, we can see that the source term of radiation is a time-dependent dipole moment or a time-dependent current element. Young Hertz in 1887 did experimentally prove that what Maxwell said was right. He was the first person to generate and detect radio waves. So his experiment consists of an oscillator circuit with megahertz frequencies, and he had a detector loop separated from the emitter through space. So I urge every young student to go and have a look at this particular experiment done by Hertz, and it's pretty inspirational. And this was the first time somebody who had shown that the electrical disturbance in one place, say here the spark plug, can generate radiation, and that can be detected away from it at a distance which is not directly electrically coupled. But so this was a direct proof of the existence of electromagnetic radiation. And this was the world's first dipole antenna, which Hertz had created. And the thing is, it is worth to look at this because a lot of the terahertz emission schemes, generation schemes of the modern day are really related to this sort of an arrangement. Hertz could detect the radio waves of megahertz frequencies during his circuits, but in order to generate electromagnetic radiation in terahertz frequencies, these circuits are really not the way to do it. These circuits cannot support such high frequencies. So what one would need is to have oscillations and transients that take place in a time scale of hundreds of femtoseconds to 10 picoseconds, ultra fast processes. So the question is, how do we generate such very short transients. Enter femtosecond lasers. These femtosecond lasers have these lasers emit pulses with a width of tens of hundreds of femtoseconds. They have a very broad spectrum. In the figure, you can see the intensity profile and its Fourier, the spectral component in the Fourier space. And the most important thing about it is that they are extremely powerful. The instantaneous powers can, they hover in the tens of gigawatts. So the thing is, there are pulse lasers with such high powers, with terawatts powers, which can be used for fusion reactors using inertial confinement. A little different from what Dr. Jinder had explained previously, but these are strong enough to initiate nonlinear optical phenomenon in material. These pulses are so strong that one could generate plasma. This white streak is a plasma in mid-air, made by just focusing the femtosecond pulse in air. These are that powerful. When at the focus point, the air molecules can instantly ionize because of the high energy density at this, and in this vicinity. And another useful thing about femtosecond pulses is that you can track ultra fast processes such as chemical reactions, electron hole recombination, carrier relaxation, which happens at a time scale of several picoseconds. So you need a shorter pulse than picosecond to study dynamics happening in picosecond time scales. So the idea is that femtosecond pulses can drive strong, ultra fast, sub-picosecond phenomena in matter. And these phenomena can generate terahertz radiation. Many materials, many semiconductors, generates terahertz radiation when it is simply shown by an amplified or a usual femtosecond pulse. So this part, until this part of the presentation, the vital point I would like to express is that femtosecond pulses drive such ultra fast phenomenon, which leads to the generation of electromagnetic waves. Let me digress for a moment. Let me talk about pulses, electromagnetic pulses. Pulses are interesting. They are made of multiple frequencies. They add up in a specific phase relation. They're wave packets. So in this figure, you can see when you have just one frequency, you have a continuous wavelength. The intensity is constant in time. As you start adding more and more modes, you get pulsing. You get sharper and dimmer regions. And in a femtosecond pulse, the number of modes you add are in tens of thousands or even millions. So if you add so many number of modes in a proper manner, in a mode locked manner, you would end up with pulses with very, very, very short pulses. So the shorter the pulse in time, broader its spectrum is. And the femtosecond laser output is a train of such pulses. And each one of those pulse is capable of generating a broadband terahertz pulse. Now I would like to focus on how an example of how it is done and how pulsed terahertz spectroscopy works. So let me just show you one example. This is an antenna. So there is a gold electrodes attached on a low temperature grown gallium arsenide, the electrodes are biased, but this is such a bad conductor that there is absolutely no current flowing. The dark currents are probably in the order of picoamperes, and there's practically nothing happening here. It's just some voltage across this. And when you excite this gap with a femtosecond pulse, you generate a large number of electron hole pairs here. So since the pulse is strong and strong, it can create a large number of electron pairs. And now this is a conducting gap, and a current happens between this current element appears here. But this current element does not stay there for long. It dies down very fast because of the choice of substrate we are using. And such current elements last for sub-picosecond time scales in the case of a material like gallium arsenide. And what we get is terahertz radiation on the other side. So in a pulsed terahertz spectroscopy system, what we directly measure is the electric field. Compared to almost all other spectroscopic arms, like infrared or visible, we measure the intensity more. But here, it's a direct measurement of electric field, which preserves the phase information. And what we see on the right is the spectrum. We can see that this particular pulse is made of so many frequency components adding in this with its own amplitudes. And I have not shown the phase information also, but it is there. And the good thing about directly measuring the electric field is that phase information is preserved. We don't have to go through tedious Kramer-Kronig analysis to find out the material parameters, and which is not the case usually with the other spectroscopic techniques. But depending on the kind of emitter you use, you get different kind of spectrums. The one from zinc telluride is rather short, but you could generate terahertz pulses from air plasma, which is very broad. You can see it almost covers the entire terahertz gap, so-called gap. So now that we have terahertz radiation at our disposal, the next thing to do is to pass it through matter. One could just pass it through air and see what the spectrum look like. With keeping that as a reference, one could pass it through materials that we want to study. You can see that when you have a thick sample in the path, the pulse shifts by a delta T amount, which depends on the refractive index of the materials and thickness of the substrate we use. And one could do a similar experiment with the on an excited sample. Excited could mean you have heated up the system, or you have generated electron hole pairs. So this can be done using another femtosecond pulse. And you can see here that the red pulse, so the pulses I show here is one through air, the blue is the one that has passed through indium nitride, and the red with a slightly lower amplitude is the one that is passed through a photo-excited indium nitride. So you can see that readily that the red pulse has a slightly lower amplitude than the blue due to terahertz radiation absorption by the electron hole pairs. And one could vary the time difference between the excitation and probing, and such spectroscopic arrangements are called optical pump terahertz probe spectroscopy. So by comparing these pulses, by looking at their FFT spectrum and measuring the transmission T of omega, one could arrive or the reflection mode, one could arrive at AC conductivity. So you get the sigma of omega of the material, mobility, refractive index, dielectric, and one could find out all these parameters about a material. The question is why, and what information are we looking at by studying such studying materials. First of all, a lot of excitations in condensed matter system happens to be in this spectral range, in the terahertz range. Many phonon modes. We know that microwave spectrum is intramolecular vibrations, but terahertz is more of the infrared spectrum is more corresponds to intramolecular vibrations, but terahertz is not as strong, but it drives intermolecular vibrations, like so phonon modes. So semiconductor energy gaps have terahertz energies and plasmons. So here we see the phonon modes in beta barium borate crystal, which is these are the peaks, the specific frequencies that are absorbed in the material. And we know that microwave spectrum corresponds to rotational transitions. So many of the polar molecules like water have a spectral fingerprint in terahertz regime. And the last one, terahertz radiation is extremely sensitive to the conductivity in material. It can act as a non-contact probe for nanoscopic conductivity in material. One could get ideas about confinement, charge confinement, disorder in the medium. So just as an example, I've shown here the terahertz spectrum from a big bulk crystal and one from a silicon nanocrystal. So they are different because the conductivity dynamics is different in these two systems. By looking at the terahertz spectrum, one can arrive at relevant conclusions from this. And talking about some of the applications, the terahertz radiation is transparent to dielectric materials with no conductivity like paper, cloth, plastic. It offers sub-millimeter spatial resolution, which is comparable to human eye. And the radiation is relatively safe. It's safer than X-ray because these are non-ionizing. The photon energy is too low to create any radiation effects. And as an example, we can see here how terahertz radiation could be applied in industries. It's extremely sensitive to polar molecules like water. On the left, there is a study of paper drying with time, studied using terahertz radiation. On the left is it's a scheme to detect diabetic foot syndrome by terahertz reflectivity. And people use terahertz radiation in conductivity mapping and imaging. And here is a conductivity map of a CVD grown graphene. And many explosives have phonon modes in terahertz region, which might help us in identifying them in security systems. And now even there are commercial systems which can do this. And right now, the experiments which I do in my lab in Institute of Physics is to look at the scattering response. The examples we saw earlier are of the transmission response or reflection response of terahertz radiation with materials. Now we combine the picosecond temporal resolution of terahertz radiation and nanometer spatial resolution of AFM tips. So in such experiments, this is probably a bit. This is an advanced version of terahertz spectroscopy, and we are basically looking at how the radiation scatters at the AFM tips. By doing so the scattering is extremely sensitive to the dielectric environment beneath the AFM tip. And by looking and mapping the scattering of a surface, you could understand the conductivity of the environment directly beneath an AFM tip. And this would help us understand conductivity in nanometer scale. Because many often when we do terahertz measurements, the information we obtain is a space averaged response of the material. We cannot focus the terahertz radiation beyond a certain limit, because the airy diameter would be very hard to be brought below, say, 0.1 millimeter or so. But here, since the scattering is most sensitive to the tip, the environment just below the tip, which is probably 10 or 20 nanometers in size, we get information in a length scale of nanometers. So such measurements can be used in analyzing circuits. It can be used in looking at the processes in devices and nanoscale materials, etc. So this is the latest work which I'm trying to do here as a part of my stay here in Prague. And I have intentionally not told you about how we detect terahertz radiation, which in itself can be lengthy and probably avoided. And now let's move to the conclusion. So what I intended to do is to familiarize you with the terahertz spectroscopy and what are the spectral fingerprints in terahertz regime, and also some of the applications of terahertz regime. And thank you for listening to me.
Thank you very much, Dr. Vaishak.
Thank you. So I would also like to thank the department for giving me this opportunity, and also wish Shukumar sir and Charlie sir all the best wishes. I wish the rest of their life is also as fruitful and energetic as it was during the time in Devagiri. Thank you.
So it was a very nice talk on terahertz spectroscopy. So, basically what happens to anyone who has a femtosecond laser in his lab, like we have here, a femtosecond amplifier. So many people have asked me, why don't you start working in terahertz spectroscopy? Because you have basically the major equipment is already there. So now what you need to buy is some suitable crystals.
Yeah.
So, we had a lot of things to do, so never really got into terahertz. So, questions from the audience, students? Any questions on this very interesting new field of spectroscopy? So I have a question. Okay. What kind of energies do you get? When you generate the terahertz pulses, so if you try to measure the energy of these pulses, where do they fall like?
Actually the efficiency is very, very low, because if you are taking the nonlinear optical route, the phase matching is not very easy to achieve. There are some techniques like tilted pulse front technique using lithium niobate, which where you observe the terahertz radiation in the Cherenkov direction. So those can give you millijoules or microjoules of power energy per pulse. I had a chance to develop one such system back in our back when I was doing my PhD, but I did not get to measure the absolute energy. We did not use a bolometer or something. We did not have that system to measure the power.
To measure the power, yes.
We did, but here in my current lab, we have measured the electric field, and that the peak electric field can come somewhere in the several kilovolts. These are strong pulses. Yeah.
I was actually wondering, like, what kind of a device you can use even for measuring the energy in the terahertz region.
Yeah. People use bolometers and what are such materials where it is sensitive to heat.
Thermopile and all that. Yeah.
Yes, exactly. Stuff like that. They do that. But that was a problem. We in the beginning we did not know what if we are generating, and we did not know how to detect them. But it was there all around us. But
it was there all around. Yes. Yeah. Very true.
Yeah.
Okay, so thank you so much, Vaishak, for the talk.
Yeah. Thank you.
And now we are coming to the last talk in the session. This is by Dr. Ashwati Balagopal. So Ashwati did BSc from St. Joseph's College, and her MSc is both in physics from IIT Madras, and she was a graduate trainee at TFR Mumbai, and then she also worked in the INO, the India-based Neutrino Observatory. Ashwati is a PhD from Karlsruhe Institute of Technology in Germany, and she worked on developing a radio array as a part of the surface air shower detectors of IceCube for the detection of PV energy gamma rays from the galactic center. And she was then a postdoc at Karlsruhe, and currently she's a postdoc in the US at the University of Wisconsin in Madison, and she works on the gravitational wave follow-up with neutrinos detected by IceCube on the global neutrino spectrum of medium energy neutrinos detected by IceCube and the mass composition of inclined air showers detected by IceTop. Ashwati.
Thank you so much for the introduction. I will start. By sharing my screen. I hope you can see the screen. Can you see?
Yes.
Yes.
Yeah.
Okay, very good. And it's in full screen mode, right?
Is it, Srikumar? Is this full screen mode?
Yes. Full screen.
Okay. So I did this old picture of our batch from when we passed out in 2012, and you can see here Srikumar sir and Charlie sir are sitting with us. So first of all, I would like to thank Srikumar sir and Charlie sir for their service and dedication. നിങ്ങളുടെയൊക്കെ സർവീസും ഇൻട്രസ്റ്റ് ഇൻ സ്റ്റുഡൻസും കാരണമാണ് ഞങ്ങൾക്കൊക്കെ എന്തെങ്കിലുമൊക്കെ അച്ചീവ് ചെയ്യാൻ പറ്റിയത് ലൈഫിൽ. സോ താങ്ക് യു സോ മച്ച്. ആൻഡ് ഞാനും എന്നെ പോലെ തന്നെ സെന്റ് ജോസഫ്സ് കോളേജ് ദേവഗിരി ഡിപ്പാർട്ട്മെന്റ് ഓഫ് ഫിസിക്സിന് പഠിച്ചുപോയ എല്ലാവരുടെയും ബിഹാഫിന്ന് ഞാൻ ഗ്രാറ്റിറ്റ്യൂഡ് അറിയിക്കുന്നു. And I wish both of you a wonderful and awesome retired life. Now I'll go into the scientific part of the presentation. So I will talk about cosmic neutrinos that we detect with the IceCube Neutrino Observatory. So the IceCube Neutrino Observatory is located at the South Pole. It is a detector setup that we have over there, which is 1 kilometer cube in volume. It looks like this if you have a 3D view of it. And what we have over there are 86 strings, which are just drilled deep into ice. And each of the string consists of 60 photomultiplier tubes, And these photomultiplier tubes are basically optical modules, optical detectors, which detect light. And what we do with these optical modules is to detect Cherenkov light, which is emitted when neutrinos interact in the ice shelf in Antarctica. I will talk more about this in detail in the coming slides. So here you can see the setup, and it is located over here in Amundsen Scott South Pole Station. Here, there is a laboratory on top, Ice Cube Lab, which actually collects all the signals from these optical modules, so collected on the surface, and then it's transmitted by satellite, and it comes to our house at the tip of our hands, and then we look at this data from this transmitted signals. There is also an array of cosmic ray detectors on the surface of Ice Cube, which is called Ice Top. And these detectors, so this array of detectors will detect cosmic rays, which is coming from all over. So all different parts of the universe will enter Earth. And then these detectors are just looking at them. So these cosmic rays are mainly background to neutrinos, which I'll explain again. This isotope detector array is used to veto these cosmic rays, and also we can do side by side a lot of cosmic ray physics with this isotope array. So this is the entire detector setup that we have at the South Pole. Now, first of all, let me go and briefly explain what neutrinos exactly are, because I'm not sure if you people know about it. So neutrinos are actually some fundamental particles. Here you have the standard model of particle physics, and these are all of the particles which constitute everything that we see around us. So this is the most fundamental particles that you can see around us. And neutrinos belong to this. So here you can see these are the neutrinos belonging to the class of leptons. And neutrinos have different types. So we have 3 types of neutrinos which are known as of now. And these types are also known as flavors. So this is some jargon. We call them flavors. And so you can see electron neutrino, muon neutrino, tau neutrino, and so on over here. And each flavor corresponds to its corresponding other lepton. So this other leptons that are existing are charged leptons, while neutrinos are chargeless. So electron neutrino corresponds to an electron, muon neutrino corresponds to a muon, and so on. Neutrinos, as I said, are chargeless. They are nearly massless. People are actually trying to find the mass of neutrinos right now, and let's hope that within the coming decades we can actually find this. Neutrinos can also oscillate. What we mean by this is that they can change flavor. So, for example, an electron neutrino can become a muon neutrino or a tau neutrino, and so on. So these are some interesting characteristics of neutrinos. But one of the most difficult things to study these neutrinos is that they are extremely, extremely difficult to detect because they rarely interact at all. So in order to detect something, you need it to first interact somehow, and then you see the resulting stuff. So if there is a charged particle, it interacts with the media, and it either has some charge deposit or it has some light that is emitted. And it is with this interaction that we actually detect these particles. So the problem with neutrinos is that they very, very rarely interact. So we don't even know that they passed us or they passed some detector or not. So once they actually do interact, which is a very rare process, then what happens is that they will produce their corresponding charged leptons.
മ്യൂട്ട് ആയെന്ന് തോന്നുന്നു. മൈക്ക് മ്യൂട്ട് ആണ് ആക്ച്വലി.
ഇപ്പൊ
ഓക്കെ ഓക്കെ കേക്കാം.
അപ്പൊ ഞാൻ ഇത്രയും നേരം പറഞ്ഞ കേട്ടില്ല.
കുറച്ചു നേരം ഇടയ്ക്ക് മ്യൂട്ടായി പോയി.
ഓ അതെയോ, ഓക്കെ ഓക്കെ. സ്ലൈഡ്സ് കാണാമോ?
യെസ്.
ഓക്കെ, വെരി ഗുഡ്. എവിടെയാ കേട്ടത്? Okay.
You are now for something like 30 seconds.
Okay.
About 30 seconds. Yes.
Okay. All right.
Yes.
So I'll once again say the last point. Neutrinos rarely interact, and because they are so rare, it's very difficult to see them. And in once these rare interactions do occur, they produce the corresponding lepton. So an electron neutrino will produce an electron, and it's with this electron signature that we can actually see that a neutrino of electron flavor actually passed a detector, and we can understand our physics based on this. So where do neutrinos occur? Neutrinos are everywhere, all around us. There are neutrinos which are remnants from the Big Bang. These are the cosmological neutrinos. So they are all around the universe from the time Big Bang occurred. There are neutrinos that come from the sun. Every day from the sun, there are neutrinos coming towards the earth and bombarding us. There are neutrinos that come from nuclear reactors. There are neutrinos that come from natural radioactive decays. They come when cosmic rays actually enter the earth, and they interact with the atmosphere and produce a lot of particles. And neutrinos are also one of the products of these kind of interactions of cosmic rays with the atmosphere. Neutrinos also are producers in the different sources, the galactic sources as well as the extragalactic sources, and they come directly from these sources towards us. So all in all, you can see it covers these wide range of energies, and it's following different kind of spectra from different kind of sources. So all in all, you have around 100 trillion neutrinos passing through your body in every second. But we are going to focus on cosmic neutrinos. So that is neutrinos that come from different cosmic accelerators in the universe. So from these accelerators, here's an example of an active galactic nuclei. Mostly there are 3 types of messengers that are emitted by these kind of sources in the universe. These are cosmic rays, gamma rays, and neutrinos. So cosmic rays are the earliest studied messengers or earliest detected messengers by mankind, and these are essentially charged particles which have masses from all the way of proton to ion. And we do detect this both from space and from Earth, and they are seen to have energies as large as 10 raised to 21 electron volt, which is really, really large. It's impossible by human beings to create anything that is this energetic themselves. So, for example, the highest energy that we have been able to achieve is around 10 raised to 12 electron volt, for these kind of particles. So these things are produced by nature's accelerators, and all of them do come towards Earth. Cosmic rays, being charged particles, will get deflected by the different magnetic field that you can see in the intergalactic space. Intergalactic space. And so they will bend a lot before reaching the Earth. So because of this, by the time they reach the Earth, we are not able to say the exact direction from which it came. So that is, it cannot point directly to their source. But as I said before, neutrinos are neutral, and also gamma rays are also neutral messengers. So with these two messengers, we can actually point back directly to the source because they do not do any bending by the time they reach the Earth. So once you know the direction from which you saw a neutrino, you know where which portion of the sky it came from. But how do we detect them? With a lot of difficulty, as I said, because they are very rarely interacting and most of them just pass through the Earth completely. So in order to have an interaction, we need to wait for a very, very long time. And once they interact, the resulting particle, as I said earlier, will be a charged product. So if you have a muon neutrino, it will interact and produce a muon. And then we detect this resulting charged particle, which is muon in this case, by its interaction with the surrounding medium. So if you have a transparent medium, then this charged particle will produce Cherenkov light, and we can detect this Cherenkov light. What exactly is Cherenkov light? When a particle, a charged particle, travels faster than the speed of light in that particular medium, it will produce a sonic boom that looks like this, and this results in Cherenkov light being emitted. And we can just look at these kind of Cherenkov light if we just have a lot of PMTs arranged like this. So this is exactly what we try to do. In order to do this, we need very large volumes because, as I said, it's really rare interaction. So we need as much chance as possible in order to detect them. And also we need transparent media because we need to actually detect the light that is emitted from them. So we don't want the light to be absorbed. So this is what is required: large volume and transparent media. Where on the Earth do we have this? We have water, different sources of water. So there are different experiments. So these are the three main experiments we have so far on Earth, which does this. One is at the Mediterranean Sea. So the huge volume of sea is our detection medium. An experiment called Antares is there. There is one in Russia. Lake Baikal experiment, again, does the same thing. And there is one in the Antarctic ice cube neutrino observatory, where instead of having water, we actually have the frozen form of water, which is ice, as our medium. So here is an aerial view of ice cube. Here's the South Pole Station, where a lot of activity happens, not just ice cube science, a lot of glaciologists and so on. They all reside over here in the South Pole Station. This hexagon shows the region that we have, where we have ice cube drilled deep into the ice. Here is a skiway where the planes land. And here you can see our tiny, I'm sorry, this is the one, a tiny ice cube lab. And just for picturization, here you can see a string that is drilled and being put deep into the ice. And you can see the optical module that is attached to the string. So you have a lot of optical modules attached to the string all the way down. So this was completed in 2011. You can see the bunch of scientists who are very happy that the experiment was completed. And once the experiment was completed, we can take data and understand the physics. So once we turned on our experiment, what does our experiment see? Here in black, you can see ice cube. This is the Earth, and here you have the South Pole. So ice cube sees a lot of atmospheric muons. Where do these come from? They come from cosmic rays which interact in the atmosphere and produce muons. So these are around 3,000 cosmic ray muons per second. So it's a huge background for us, and we have to reject this. So from the other side of the Earth as well, cosmic rays will be interacting. And as I said earlier, these interactions also produce neutrinos. We call them atmospheric neutrinos. And they also pass all the way down through the Earth and will reach our South Pole. And sometimes they do produce light in our detector. And so this is not what we want to see, because these are atmospheric neutrinos and these are also background for us. So we see around 1 atmospheric neutrino in 10 seconds in our detector. And among all of this, we have to hunt for our astrophysical neutrinos, which can either come from the other side of the Earth or from this side of the Earth. Here is an example cosmic ray event that we see almost every other day in our detector. You can see that it has passed all the way down. It has lit up the surface cosmic ray array iSTOP. You can see that all stations can see, a lot of stations on iSTOP can see the light. And there is also a track of muon from the cosmic ray event, which passes through our deep in-eyes detector. And you can see that this has lit up the optical modules inside the eyes as well. So this is the sort of event that we want to reject if we want to actually detect neutrinos. So once we started taking data, we actually were able to successfully find astrophysical neutrinos of ultra high energy. So in 2012, IceCube found 2 extraterrestrial neutrinos with energies close to 1 PeV. This is 10 raised to 15 electron volt. These are the 2 famous events from IceCube called Bert and Ernie from Sesame Street. Because someone thought that it looks like them. So they named it Bert and Ernie. And this actually opened a new universe to us where we were confident that we could actually see astrophysical neutrinos and try to understand the flux of these astrophysical neutrinos, which is what we were able to do after taking a lot of data. So this was published in 2017. So you can imagine the amount of time it took to produce this. We found the astrophysical neutrino flux, and so you can see it sticking out over here in between all of the atmospheric flux that we see on the left-hand side over here. And we also found the shape of this astrophysical spectrum. So what is the power of this with respect to energy? It follows a shape of e raised to 2.8 at energies above 100 TeV. What other stuff can we do with this? We are also able to do neutrino astronomy with it. So with 10 years of IceCube data, we scanned the different parts of the sky and saw that this is the neutrino sky that we see from all around. And we do not see any one particular source which is producing most of the neutrinos that we see. It's a lot of sources that's combining. We saw that the most significant source is lying over here. It's a galaxy, which is NGC 1068. It is not a discovery yet because you need a lot of signals from one particular direction in order to call a discovery. This is just the most significant source that we see. And what we also do is to give out some real-time alerts. So once IceCube sees a high-energy neutrino from one particular direction, we immediately send out a notice saying that we saw this neutrino. Can you please look in this direction to see if you are source? So this notice is sent to AMON. It's a center that collects information from all different observatories in the world, and AMON will then send out a notice to the other observatories. So for example, gamma ray observatories, X-ray observatories, and so on. And all of these telescopes would then try to look in that particular direction to see if we can all see one particular source in tandem. So this is our first successful event that happened in 2017. IceCube sent an alert about a high energy neutrino that we saw. So this was 290 TeV. And once IceCube sent this notice, SWIFT, which is an X-ray satellite, looked at this particular direction and it started seeing something. So then it told the others, I'm seeing something. Then others also started turning in this direction. Fermi turned in that direction. Magic turned in that direction. These are all gamma ray detectors. So we have X-ray detectors, gamma ray detectors, all of them looking at the same thing at the same time. And Magic found a correlated flare of gamma rays from that direction. Fermi actually, which is a much better, higher resolution than Magic, saw that there is a flaring blazar coming from that direction. Blazar is actually a source, which is an active galactic nuclei, where the jet from the source is actually pointing directly towards the Earth. So that's why you can see the flare very nicely. And this was the famous event, Texas 0506, 056, which was detected by all of these detectors. So, as I said, this is the first detection of the same source by different telescopes, and that too by using different messengers, so neutrinos, gamma rays, X-rays, and so on. So at one particular time, we had 27 observatories from all around the Earth looking at the same direction at the same time and watching this source. So this actually brings out a new exciting era of multi-messenger astrophysics, where we can use the different techniques that we have all around in the universe and study the sources and have better understanding of our universe. I will not go into more details about what IceCube does and what all things we learn with IceCube. I will just stop over here by saying that this is a collaborative effort with more than 300 people from 53 institutions in 12 countries. So you can see all of them spread out over here. And it is the joint effort from all professors, PhD students, postdocs, master students, bachelor students, everyone together that makes this successful. Thank you so much. And once again, I would like to say thanks to Srikumar sir and Charlie sir, and all my best wishes to them. Thank you.
Thank you very much, Dr. Ashwati. That was a fantastic talk. I guess there may be questions. So, questions from the audience?
Hi, I'm Jindo here. Probably sorry to ask a stupid question in the early morning for Ashwati. Because okay. So, in one of your slides, you were shown that there are different energies for this neutrino. I was wondering, why this? This size. Okay. Yeah. And what does it mean actually, and how these neutrinos are getting different energies? Because something. Maybe it's a stupid question, so you can even say that what it is.
No, it's not a stupid question. There is no stupid question. So it actually gets the energy from its source. So whatever process produced the neutrino, it gets that energy. So for example, from let's say the case of solar neutrinos. So there are fusion activities happening in the sun. And depending on what the energy of the particles were that fuse, it's neutrino is a byproduct of that. So it's if something had what is this over here? MEV energy while the fusion was happening, then it gives an MEV energy to the neutrino. So it's just dependent on what process was happening there.
What is it, in which way that neutrino, that energy is manifested? Like, for example, for electron, let us say that there has got different velocity. Like, when we have a keV electron, 100 keV electron, you're just seeing that, okay, the velocity is more. So in which way for neutrino, this is going to get manifested on that?
Yeah, so good question. So in neutrinos, actually, we have to sort of find out what was the energy, because as I said, we cannot see the neutrino as it is. So the neutrino will interact and produce its corresponding particle, and we actually measure the energy of the corresponding particle and try to figure out what the energy of the neutrino was. So this is why we do need a lot of simulations. We simulate a lot of neutrinos of different given energies and see what byproduct, the energy of the byproduct would be. And it's with this mapping that we can actually estimate the energy of the neutrinos.
Okay, thank you. It was a really interesting experiment to experiment and talk. Thanks.
No problem. Thank you for listening.
So do you use something like a cloud chamber or some modern version of that to find out the energy of the byproduct?
As I said, we use the PMTs. So the PMTs will measure the light, and it's with this light signal that we actually understand the energy. Yeah. One second, my laptop is dying. I need to just charge it. Sorry about that.
Yeah, sure.
Yes, I'm back. Sorry about that.
Yeah, and it is so sensitive that they can detect even one neutrino, isn't it?
Yeah, definitely. We can detect one neutrino. So what a normal event looks like is, sorry, I don't have a slide of that. So you can see this, right? So along with this, there will be a lot of lit up optical modules all around, which will be noise. So we actually have to get rid of the noise as well, and then get this nice event out of it. So there's a lot of process that goes behind that as well.
A lot of signal processing.
Yeah.
Very nice. So any other questions?
Ma'am, hi.
Yes.
I have a very small doubt.
Yeah, please go ahead.
Ma'am, though there are lots of events happening in the cosmos, like a lot of fusion, as you said, why are neutrinos very difficult to detect on Earth?
Yeah, so as I said, neutrinos are chargeless particles, massless particles, and they are what we call as weakly interacting particles. So we can only see anything if they interact with our media. Since they rarely interact, they are, let's call, lazy particles that don't want to interact with anything. And so because of this, we cannot really see them a lot. It's very rare. I hope that, yeah.
And about one of the earlier slides about the experimental structure, you said there were 86 rods. Rod something. That's where I entered.
Yeah. 86 strings.
Yeah, strings. What's with the 86 number?
It's so we initially started with 80 and so it's essentially related to funding, right? We had funding for 80 strings and we put 80 strings, and then there were some leftover strings with modules that we had, so we said, okay, we have 6 more, let's just put them also. That's it.
So it's like the more the better.
Yeah, of course, the more the better. Actually, I don't have a slide right now about it. I did not go into that. We are actually expanding to a much larger volume now, because we have understood that this works, and we need a larger detector in order to detect higher energy neutrinos. So we are expanding now to a much larger volume.
Okay, ma'am. Thank you.
Just a small question. To Ashwati. Was a very good presentation. So what I want to ask is, what you measure is the Cherenkov radiation that comes out of that's the thing you measure.
Yes, exactly. That's what we measure.
Do you just look at the intensity, or are you interested in the what frequency of light is being produced, and what angular distribution will be there? But is it that?
Yeah, so we look at the charge deficit and the timestamp. These are the two information that we get from this. So the waveform of the signal, the charge deficit, the total charge deposited, and the timestamp. So it is with all of this that we actually estimate the energy and the direction of the particle.
Okay.
Yeah.
All right. Thank you.
Okay, thank you. So I guess there are no further questions. So let's thank the speaker, Dr. Ashwati, once again. And so with that, we have come to the end of the scientific session. So now over to the organizers.
Thank you all for the resource persons. I would request you to kindly note that the link to submit your feedback will be provided on the chat box. Please give us your valuable suggestions and opinion. I invite Ms. Aparna N., the Assistant Professor, Department of Physics of St. Joseph College, to deliver a vote of thanks.
Good afternoon, everybody over here. Respected Chair for the session, Dr. Reggie Philip, our most valued invited guest, Dr. Jinto Thomas, Dr. Sujin Babu, Dr. Karina B. Maliekal, Dr. Vaishak CP, Dr. Ashwati Balagopal, our guests of honor, Professor Charlie Kattakayam, Dr. R. Srikumar, my dear colleagues and all the participants. It's my privilege to propose vote of thanks on this occasion. I, on behalf of the Department of Physics, St. Joseph's College, Devagiri, extend a hearty vote of thanks to all the delegates of the webinar for their presence and contribution to make this webinar exemplary. It's our privilege to have a distinguished personality like Dr. Reggie Philip to chair our session. I, on behalf of the Department of Physics and the staffs, and on my own behalf, extend a hearty vote of thanks to Dr. Reggie Philip to take time out of his busy schedule to be a part of the event. We are extremely glad that all the speakers are our alumni, and when we approached them for delivering the talk for the webinar, they all immediately responded very warmly without any reluctance to be a part of the webinar. I would like to mention my deep sense of appreciation to all the speakers for their concern towards their mother institution. All the talks were highly informative and inspiring to the students. Department of Physics would like to express our gratitude to all the speakers, Dr. Jinto Thomas, Dr. Sujin Babu, Dr. Karina B. Maliekal, Dr. Vaishak CP, and Dr. Ashwati Balagopal for inspiring and encouraging our students. I would like to thank Professor Charlie Kattakayam and Dr. R. Srikumar for being with us and supporting us. I must not forget to thank my colleagues and volunteers for working hard to make this webinar successful. Finally, thank you to all the participants, including alumni, faculty members, and students from other institutions, my colleagues, and my students who attended the webinar for your attention and active participation. Thank you everyone once again for making this a great success. Thank you.
Thank you very much. And I would just like to thank the organizers, including Dr. Aparna, Dr. Merrill, and everybody else for inviting me here to chair the session. It was a very interesting experience, very good talks, excellent speakers. So thanks a lot for this opportunity.
Thank you, sir. Thank you for joining us.
Thank you.